3I Atlas might look like nothing more than a faint blur of light against the stars. To the naked eye, it would pass unnoticed, no brighter than the countless specks that dot the night sky. But behind that faint glow lies something extraordinary and perhaps unsettling. Atlas is not from here. It does not belong to our solar system. It is an interstellar traveler crossing the vast emptiness between stars, and it may be one of the most dangerous visitors in history. Not dangerous in the way a crashing asteroid threatens Earth, though that image is hard to resist. Its orbit will not bring it near enough to collide with us. The danger is subtler, stranger, and more difficult to dismiss. Atlas challenges our science, defies our expectations, and forces us to consider possibilities we are not fully prepared for. Its chemistry is unlike any comet we've seen. Its speed is beyond anything familiar. Its survival across billions of years raises questions about what else might be drifting in the darkness. And in its silence, Atlas mirrors us. How we react to it, whether with curiosity, fear, or denial, may reveal more about humanity than about the comet itself. In this way, Atlas becomes more than an object. It is a test, a messenger, a reminder that the universe refuses to be simple. This is the story of 3I Atlas, where it came from, what it carries with it, and why it may be far more dangerous than we imagine. Not because of what it will do to us, but because of what it shows us about ourselves and the fragile illusions we hold as we drift through the cosmos. The discovery of 3I Atlas. On a quiet night in early July of 2025, a telescope in Chile scanned the heavens the way it always does. This particular telescope, part of the Atlas survey, was designed to keep an eye on the skies for anything out of the ordinary, mostly to look for asteroids that could one day pose a danger to Earth. The astronomers and technicians working with it didn't expect to find anything beyond the usual suspects. Small rocks tumbling around our solar system, comets making their slow arcs, or space debris catching the sunlight. But on July 1st, one speck of light stood out. At first glance, it seemed almost trivial, like a dust mote floating across the lens. Yet, when its trajectory was mapped, something astonishing came into view. This was no ordinary rock. The speck wasn't circling the sun in an ellipse like our planets or comets normally do. Instead, it was traveling on a hyperbolic path, an escape route that meant it didn't belong here. It wasn't bound to our star at all. It came from somewhere else, another corner of the galaxy entirely, and it was simply passing through. That was the moment humanity discovered its third confirmed interstellar visitor, now called 3I Atlas. For astronomers, the naming of an object often feels like the start of a story, a way of grounding something cosmic and incomprehensible into human language. The 3I means it's the third confirmed interstellar object ever observed, following Oumuamua in 2017 and 2I/Borisov in 2019. Atlas refers to the telescope that first spotted it. Together, the name carries both the weight of discovery and the legacy of technology. The human effort to watch the sky carefully enough to notice something unusual. It's worth pausing here, because the idea of an interstellar object might sound abstract, even remote. But imagine for a moment standing at an airport and watching planes land. Most of them come from nearby cities, Los Angeles, Chicago, Dallas, places you know. Every so often, though, a plane might touch down from across an ocean, from Tokyo or London. Its passengers and crew have lived in a completely different context, under different skies, with different histories. That's what 3I Atlas represents. Not a neighbor from the next town over, but a traveler from across the galaxy. It carries with it the chemistry, the history, and the secrets of wherever it once formed. When Oumuamua was first detected, it shocked scientists with its shape and strange acceleration, sparking debates about whether it was even natural. 2I/Borisov, on the other hand, looked much more like a normal comet, trailing gas and dust behind it as it passed through our solar system. And now comes Atlas, different again, with its own peculiarities that refuse to fit neatly into our existing boxes. Each new interstellar visitor feels like a new chapter in a book that humanity has only just begun to read. The discovery itself was deceptively quiet. No alarms sounded, no dramatic movie soundtrack played. A handful of astronomers saw the unusual trajectory and knew instantly what it meant. But to the wider world, the news trickled out slowly. Headlines appeared, some technical, some sensational. Words like interstellar, alien, and mystery appeared in bold letters. For many people, the first reaction wasn't fear, but wonder. We were being reminded once again that our solar system is not isolated. Objects wander in from other stars, unseen until the moment they pass close enough for our instruments to catch them. If you try to imagine the scale of this, it helps to think of your own neighborhood. Picture your street with familiar houses and sidewalks. Every so often, a stranger might walk through, not stopping, not belonging to your community, but simply passing by. That's how astronomers see Atlas, a stranger walking through our galactic neighborhood, here for only a brief moment before continuing on a journey we can barely comprehend. Of course, the discovery raised immediate questions. Where did it come from? How long had it been traveling through the dark? What secrets might be hidden inside its icy core? Unlike asteroids or comets that belong to our sun, interstellar objects bring with them the fingerprints of other places. Their chemical makeup, their speed, even the angle from which they approach, all are clues that might reveal not just their story, but something about the wider galaxy itself. As astronomers traced its orbit backward, they found no exact star system of origin. Atlas may have been ejected billions of years ago during the birth of some distant star, flung into the abyss by gravity and left to wander. It may have passed through countless systems before ours, brushing past planets and stars, invisible until this moment when chance placed it in our path. In that way, it is a messenger from deep time, carrying in its atoms the record of an era before Earth even existed. The strangeness of 3I Atlas isn't just in its trajectory or its chemistry, but in what it symbolizes. To see it is to be reminded of how vast and interconnected the galaxy is. For most of human history, the night sky looked still, a dome of unchanging stars. Only in the past century have we begun to notice the constant movement, galaxies colliding, planets orbiting, comets streaking by. And now, visitors from other suns crossing into our domain, proof that the void between stars is not empty after all. For scientists, each detection is a puzzle piece. For the rest of us, it is something more emotional, a reminder that we are part of a much larger story. Think of watching a ship appear on the horizon from a foreign land. You don't know what's on board, you don't know what journeys it has endured, but its very presence sparks the imagination. What have its sails seen? What songs were sung on its decks? What storms has it survived? That's what Atlas is for us, a cosmic ship drifting silently but carrying untold histories. As the news spread, curiosity grew. Telescopes around the world turned their gaze toward it. The Hubble Space Telescope captured images of its coma, the faint glow that surrounds it as it sheds gas and dust. The James Webb Space Telescope added details about its chemical fingerprint, revealing carbon dioxide in quantities no one expected. Radio telescopes listened for any unusual signals, though they found only silence. Every observation added layers to the mystery, deepening rather than solving it. And yet, despite the questions, there is a calmness in the way scientists talk about it. Atlas is no threat. It will not strike Earth. Its closest approach will still leave it hundreds of millions of kilometers away. In that sense, it is like a passerby who never even steps onto your porch, just walks past the end of the street before disappearing again. The fascination lies not in danger, but in possibility, in the sense that something so foreign could enter our world, however briefly. So the discovery of 3I Atlas is not just a story of numbers and telescopes. It is a story about wonder, about the universe reminding us that it is bigger, stranger, and far older than our daily lives suggest. When astronomers in Chile noticed that faint speck, they opened a doorway to questions we may not yet know how to answer. Questions about life, about time, about whether our solar system is just one stop on a cosmic highway that countless travelers use. As Atlas continues its journey inward toward the sun, growing brighter, shedding more of itself into space, the world watches. Some people dream about alien probes, others see only a natural comet, but all of us, in one way or another, are drawn to the mystery. A tiny speck of light has become a reminder that the stars are not silent. They send us visitors, they send us stories, and as we trace Atlas across the sky, we wait to see what story this one will tell. When most of us think about comets, we picture something familiar, a small icy body orbiting our sun, with a glowing tail that streaks across the night sky once every few decades. These are the kinds of comets that have inspired myths, frightened kings, and delighted skywatchers for thousands of years. Halley's Comet, for instance, has been recorded since ancient times, faithfully returning every 76 years, visible to countless generations who saw the same cosmic traveller come back again and again. But 3I Atlas is nothing like Halley's Comet. It does not belong to the Sun. It is not tethered to our solar system by gravity. Instead, it comes from somewhere far beyond, wandering through the galaxy on a path that is not closed but open, hyperbolic, destined to pass through and never return. This simple fact makes it different from almost everything we usually study in astronomy. To call it interstellar is to say it carries with it the signature of another star, another birthplace, another corner of the Milky Way. Imagine standing in your backyard. Most of the birds you see are locals, sparrows, cardinals, maybe a crow. They live here, breed here, and return each season. But once in a while, you might notice a bird that doesn't belong, one that has travelled across an ocean, guided by instincts you can barely imagine. Its feathers, its songs, its very presence carry hints of distant landscapes you will never see. That's what it means when astronomers say Atlas is interstellar. It is a migratory bird of the galaxy, carrying the DNA of another sky. To understand why this is such a profound difference, it helps to think about the comets we know best. Most comets orbit in predictable paths, some swinging in close to the sun before retreating to the deep freeze of the Oort cloud, a vast reservoir of icy bodies that stretches almost a light year away. These comets are ancient, leftovers from the formation of our solar system, but they are still ours. Their orbits, however long, still tie them to the sun's gravity. Atlas, by contrast, is not bound. Its orbit is not an ellipse, but a hyperbola, a curve that never closes. If you plotted it on a piece of paper, you would see a wide arc that swoops in close to the sun before swinging back out into the galaxy, never to return. That trajectory alone is a clue to its foreign nature. Nothing native to the solar system can sustain such a path without eventually being drawn back. Only something that originated elsewhere could have such freedom. And then there is its speed. Atlas is moving at more than 130,000 miles per hour, fast enough to cross the entire United States in less than 3 minutes. This isn't just fast by our standards, It's vast even by cosmic ones. It tells us that the comet was flung out of its home system long ago, perhaps during the violent birth of a star, when giant planets shuffled debris and hurled smaller objects outward like marbles scattering across a floor. Once thrown into interstellar space, the comet became a wanderer, its fate no longer tied to any one star, only to the vast gravitational fields of the galaxy itself. Think of tossing a pebble into a river. Most stones you throw land near the shore, but every now and then one bounces and skips all the way across, carried far away by the current. That is what happened to Atlas. It was once just another piece of ice and rock in a planetary nursery, until a gravitational push sent it out into the current of the Milky Way, where it drifted for eons until crossing paths with our own sun. The chemistry of Atlas also reminds us of its alien origin. Unlike most comets we know, which are dominated by water, ice and dust, Atlas shows unusually high concentrations of carbon dioxide. That simple detail tells us it formed under conditions different from those in our solar system. Around its parent star, the temperatures, the radiation, the balance of gases, all must have been unique. Atlas is not just a rock, it is a sample of another world's building blocks. When scientists look at its spectrum through telescopes, they are, in a sense, tasting the flavors of another kitchen, one that cooked planets under unfamiliar recipes. But perhaps the most intriguing thing about calling Atlas interstellar is not what it tells us about the object itself, but what it suggests about the galaxy. If this is the third interstellar visitor we've spotted in just a handful of years, then space must be full of them. Countless comets and asteroids flung free from their homes, crisscrossing the galaxy like anonymous travelers on a highway. Until recently, we didn't have the technology to notice them. Now, with more powerful telescopes and surveys, they are starting to appear, one after another, as if we've finally lifted a veil and discovered a bustling crowd in what we thought was an empty room. It's humbling to think about. For centuries, we believed our solar system was an island, largely self-contained. Then we learned about exoplanets, proving that other stars have their own worlds. And now, these interstellar comets arrive as physical proof that the boundaries between systems are porous. Material leaks across them. A rock formed around a star 100 light-years away can, billions of years later, drift past Earth. It makes the galaxy feel smaller, more connected, almost like a neighborhood where doors are left ajar and visitors come and go. For the average person, it can feel abstract. Stars and galaxies are hard to imagine at human scale. But picture this. You're walking down a quiet street in your hometown. Most of the cars you see are ones you recognize, the same makes and models your neighbors drive. But then, suddenly, a foreign car rolls by, one with license plates from another country, its design unlike anything sold here. You don't know its story, but you know immediately that it came from somewhere far away. That is the experience astronomers have with Atlas. And so, when we call it a journey from the stars, we mean that literally. Atlas is not just moving through space, it has carried itself across unimaginable distances, shaped by a history we can only guess at. Perhaps it formed near a young star, alongside planets that never survived. Perhaps it drifted past supernovae that bathed it in radiation. Perhaps it passed other civilizations, unseen, unremarked, as it wandered in silence. Each possibility adds to its mystique. What matters most is that we have the rare chance to glimpse it now as it cuts across our corner of the galaxy. We cannot stop it, we cannot redirect it. All we can do is watch, measure and wonder. To see Atlas is to be reminded that the universe is alive with motion, that we are not alone in hosting cosmic visitors, and that even the emptiest stretches of interstellar space are full of travelers making their slow, endless way. This visitor, unlike any comet bound to our sun, offers us a chance to look beyond ourselves. It reminds us that our solar system is not the center of the story, but one chapter in a much larger book. And as Atlas drifts past, glowing faintly in the night sky, it whispers of distant beginnings, of stars we may never see, and of the journeys that carry across time longer than all of human history combined. Speed beyond imagination. There's something almost hypnotic about thinking of speed in space. On Earth, we measure speed in ways that feel impressive to us. Cars pushing past 70 miles per hour on the highway, airplanes cruising at 500 miles per hour, or rockets tearing through the atmosphere at several thousand. But when it comes to cosmic objects, these numbers seem almost laughable. Out there, speed becomes a different language, one that stretches our imagination far beyond anything we've ever experienced. 3i Atlas speaks that language fluently. When astronomers measured its velocity, they found that it was moving through the solar system at a staggering 130,000 miles per hour, nearly twice as fast as its interstellar predecessors, Oumuamua in 2017 and 2I/Borisov in 2019. To put that into perspective, it's fast enough to cross the continental United States in under 3 minutes. Imagine standing on the East Coast, watching something appear on the horizon, and then realizing it had already vanished beyond the West Coast before you had time to take a breath. That's the scale we're talking about. Speed in space isn't just a matter of numbers. It's a story. Every fast-moving object carries with it the memory of what launched it, of the forces that set it free. In the case of 3i Atlas, its breakneck velocity tells us about violent beginnings, about gravitational encounters and cosmic slingshots powerful enough to fling a body from its home star system into the infinite dark. It's as though we're watching the aftermath of some ancient accident, the comet itself forever locked into a path of exile. Why is Atlas faster than Oumuamua or Borisov? One explanation may lie in where it came from. Comets are often born in the cold outskirts of planetary systems, places where giant planets exert a gravitational grip strong enough to act like slingshots. When a comet drifts too close to one of these massive worlds, imagine a Jupiter many times the size of our own, the encounter can hurl it outward at incredible speeds. Sometimes the comet remains bound, swinging back in elongated orbits. But sometimes the encounter provides just enough push to send it over the escape threshold. Once that happens, the comet doesn't just leave its home, it leaves forever. Think of a marble rolling around in a bowl. Most marbles wobble back and forth, trapped by the curve, always returning toward the center. But if you push one hard enough, with just the right force, it skips over the edge and never comes back. That is what happened to Atlas long ago. Except instead of a bowl and a marble, it was a young star system and a colossal planet. The push it received was so violent, so decisive, that even billions of years later, the comet still carries the momentum of that single encounter. Another possibility is that Atlas has been gaining speed from multiple encounters. Over its journey through the galaxy, it may have passed near other stars, other planets, and other massive objects, each one giving it a tiny tug, a subtle nudge. Over millions or billions of years, those nudges add up. It's like a pinball bouncing between bumpers, each collision sending it flying faster and further until it's impossible to track its original path. By the time it reached us, Atlas had accumulated a velocity unmatched by the previous interstellar visitors we've seen. There's something poetic in this. Atlas is not a quiet traveler, it's a runaway. Its speed is the evidence of an origin written in chaos, a reminder that the universe is constantly reshaping itself through violence as much as through calm. Stars are born, planets collide, debris scatters, and out of that, now and then, an object is flung into interstellar exile, moving so fast that nothing, not even the gravity of another star, can ever reclaim it. For scientists, speed is also a tool. The velocity of Atlas allows us to calculate its excess speed, the measure of how fast it moves, even after accounting for the Sun's gravitational pull. This number, known as its hyperbolic excess velocity, sits around 61 kilometers per second, nearly double what Oumuamua carried. That's not just trivia, it's a fingerprint. It tells astronomers that this object came from far beyond our neighborhood, that its story began in environments more energetic, more chaotic than the ones that shaped our solar system. But for most of us, speed is best understood through comparison. Imagine the International Space Station circling Earth at about 17,500 miles per hour, fast enough to lap the planet every 90 minutes. Yet Atlas is moving nearly 8 times faster. Imagine Voyager 1, humanity's most distant spacecraft, drifting at about 38,000 miles per hour, and then realize that Atlas is traveling more than 3 times that speed. It makes even our greatest achievements look slow, like a child's bicycle next to a race car. This speed also affects how we experience the object. Because Atlas moves so fast, our window to observe it is incredibly brief. It is like a train rushing past a station. You can catch a glimpse, maybe snap a photo, but then it's gone, fading into the distance before you can process what you've seen. That fleeting quality is part of its allure. We are watching something ancient, something formed before our solar system, but we are only allowed a passing glance before it vanishes back into the night. The implications of this speed stretch beyond science into philosophy. In a way, Atlas embodies the restless energy of the universe. It refuses to be captured, refuses to linger. It is the cosmic equivalent of a traveler who never stops moving, never settles down, always carrying with them the memory of distant places. Its velocity is not just a number, it's a character trait, a defining feature of its existence. And yet, for all its power, Atlas is fragile too. Comets are not solid rocks, but loose conglomerations of ice, dust, and stone. They are sometimes called dirty snowballs, held together more by gravity and cold than by strength. To think of such a delicate body racing through the galaxy at 130,000 miles per hour is almost absurd. It's like imagining a snowflake caught in a hurricane, somehow refusing to fall apart. That endurance is part of its mystery. How has it survived so long, so fast, without being shattered into dust by collisions or cosmic radiation? Perhaps that is why people can't help but wonder about meanings beyond the natural. Some ask, could an object moving this fast, this precisely, be more than a comet? Could its speed itself be a kind of signature, a sign of intent rather than accident? The evidence so far points toward natural explanations. But the imagination lingers, because speed at this scale feels purposeful, even when it isn't. What we know for certain is this: Atlas carries within its motion the story of its birth. Somewhere, long ago, a gravitational encounter hurled it outward with such force that even across billions of years, it still hasn't slowed. To watch it pass is to watch the aftermath of that ancient violence playing out before our eyes in silence and light. And so, when we look at Atlas streaking across the solar system faster than anything we've ever seen, we are reminded that speed is not just about numbers on a chart. It is about stories of origin, of exile, of endurance. It is about the restless energy of the galaxy itself, expressed in the motion of a single icy traveller. And as Atlas rushes past, never to return, it invites us to reflect on our own place in that movement, on the ways in which we too are carried by forces we barely understand, rushing forward into the future, unable to turn back. The hyperbolic signature. When astronomers first plotted the path of 3I Atlas across the sky, they noticed something unusual almost immediately. Its trajectory was not curved like the familiar ellipses of comets and planets that belong to our sun's domain. Instead, it traced a sweeping arc that looked open-ended, a curve that never closes in on itself. This is what scientists call a hyperbolic orbit, a shape that reveals not just where an object is going, but also something profound about where it came from. To understand why this is important, it helps to think about orbits in everyday terms. Imagine tying a ball to a string and swinging it around your hand. The ball goes in a circle, always pulled back by the string, unable to escape. That's what planets do around the sun. They move endlessly in loops, bound by gravity. If you cut the string, the ball would fly off in a straight line, never to return. But space isn't empty. It's full of other forces, and so instead of straight lines, freed objects often trace hyperbolas, graceful open arcs that signal escape. Most comets we know are like the ball still tied to the string. They come close, glow with tails of dust and ice, and then retreat into the outer darkness, but always with the promise of return. Halley's Comet, for instance, is famous precisely because we can count on seeing it again. Its orbit is an ellipse, a closed loop, so even if it takes decades, gravity ensures it will circle back. But Atlas is different. Its orbit is not a closed loop, but a wide-open door. Its path tells us that it is not owned by our sun and never was. It entered our solar system from beyond, dipped in for a brief encounter, and will leave again forever. That is what hyperbolic trajectories tell us. They are signatures of the truly foreign, the travelers that belong to no star but wander between them. The mathematics behind this are deceptively simple. Every object moving around the sun can be described by something called orbital eccentricity. For a perfect circle, that eccentricity is 0. For an ellipse, it's somewhere between 0 and 1. For a parabola, the exact boundary between bound and unbound, it is exactly 1. Anything greater than 1, however, is hyperbolic. It means escape. It means freedom. Atlas's eccentricity is comfortably greater than 1, making it not just a visitor, but an interstellar one. But beyond the numbers lies a story. A hyperbolic path is a footprint of cosmic violence. To fling a comet onto such a trajectory, something had to happen in its past, something dramatic enough to overcome the gravitational tether of its home star. Often, this means a close brush with a giant planet, like a cosmic billiard ball collision that sends it outward with enough speed to break free. Other times, it might be the gravitational tug of neighboring stars in a crowded nursery where solar systems are born. In either case, the result is the same: exile. The comet is banished to the galaxy at large, a permanent wanderer. If you think about it in human terms, it's a bit like moving away from your hometown. Most people live their whole lives within some loop of familiarity, circling back to the places they know, like elliptical orbits. But a few leave for good. They board a train or a plane and travel so far that return becomes impossible. They may send postcards, they may be remembered in stories, but they will not come back. Atlas is like that, an exile whose path is forever open. And what does this mean for us watching from Earth? It means that our encounter with Atlas is fleeting. Unlike Halley's Comet or Encke's Comet, we cannot mark our calendars for its return. Once it departs, it is gone forever, carrying with it whatever secrets it holds about its distant birthplace. Our only chance to study it is now, during this brief passage, before it fades into the black again. This impermanence is part of the beauty. There is a bittersweet quality to watching a hyperbolic visitor. We know we will never see it again, and that makes every observation precious. It's not unlike meeting a traveller at a train station, striking up a brief conversation, and then watching them vanish into the crowd, knowing your paths will never cross again. The value lies in the moment itself, in the rare chance to connect across distance. Hyperbolic trajectories also teach us something about the galaxy as a whole. If Atlas is here, And if Oumuamua and Borisov came before it, then these wanderers are not rare accidents, but part of a larger pattern. Every star system, including ours, produces debris during its formation. Some of that debris stays local, bound in elliptical orbits. But some is inevitably ejected, set free to wander indefinitely. Over the lifetime of the galaxy, this has created a vast, invisible population of interstellar nomads, comets, asteroids, fragments, all moving on hyperbolic paths through the void. What we're seeing now is not an exception, but a glimpse into that hidden ocean of motion. There's another way to think of this. Imagine standing at the edge of a forest path. You see one hiker emerge from the trees, then another, then a third. At first, you think it's coincidence, but then you realize the path is busy and you've simply been looking away until now. That's how astronomers see these interstellar visitors. For most of human history, we lacked the tools to notice them. Now, with powerful surveys scanning the skies every night, we're finally catching glimpses of the traffic that has always been there. Hyperbolic paths are the telltale footprints of that hidden flow. And yet, there's mystery here too. A hyperbolic orbit looks natural, but could it be deliberate? Some have wondered whether an object like Atlas could be designed to mimic such a path, to appear natural while carrying out a mission. The speculation may sound far-fetched, but it lingers in the imagination. After all, what better disguise for a probe than to follow the same trajectories as countless natural wanderers? To hide among the noise is the perfect camouflage. Whether Atlas is simply a comet or something more, its hyperbolic path provides the cover. Even setting aside speculation, the sheer elegance of the orbit is enough to inspire awe. To picture Atlas approaching from deep space, curving past the sun, and then continuing outward, is to picture a dance choreographed not by humans, but by gravity itself. It is a movement so vast, so precise, that it feels like a kind of cosmic music, one that plays whether or not we are listening. And so, when we say that Atlas will never return, it is both a statement of science and a reminder of impermanence. We are witnessing something transient, a brief crossing of paths in a galaxy filled with endless wanderers. For astronomers, the hyperbolic signature is a tool for classification. For the rest of us, it is a symbol of journeys without end, of the way the universe carries its travelers across unimaginable distances without ever looking back. Atlas will leave us soon, receding into the darkness, its hyperbolic path carrying it to places we will never follow. And yet, in the short time it spends here, it leaves behind more than data. It leaves behind a feeling, the sense of having brushed against something vast and unknowable, a reminder that the universe is not static but alive with motion, forever sending its wanderers across our sky. The hidden chemistry. When the James Webb Space Telescope turned its gaze toward 3I Atlas, astronomers expected to see something familiar. After all, comets, whether from our solar system or beyond, tend to follow a script. They are icy time capsules, their surfaces warming as they approach a star, releasing water vapor, carbon monoxide, a little carbon dioxide, and assorted dust. The ratios may vary, but the pattern is recognizable. It's the sort of thing astronomers can almost predict with pencil and paper before the data arrives. But when Webb's instruments captured the spectrum of Atlas, the results were startling. Instead of the expected signature dominated by water, the telescope revealed that the comet's coma, the glowing cloud of gas and dust surrounding its core, was filled primarily with carbon dioxide, not just a little more than usual, but overwhelmingly so. Early readings suggested a CO2 to water ratio close to 8:1. For context, most comets in our solar system are dominated by water vapor, with CO2 playing a supporting role. Here, that order was reversed in dramatic fashion. This discovery rattled expectations. For decades, scientists have assumed that water ice is the dominant player in cometary chemistry. It makes sense. Water is abundant in the solar system, and the distances at which comets typically form favor its preservation. Even Oumuamua, though it was never observed to release much gas, was thought to have water ice beneath its surface. But Atlas broke the mold. At over 3 astronomical units from the Sun, farther than Mars, when most comets would still be largely inert, it was already venting carbon dioxide in quantities large enough to be detected from Earth's orbit. It's as if you opened a cookbook expecting bread and found a recipe for something you didn't even know existed. The basic ingredients were there, but the proportions made no sense. Why so much carbon dioxide? Why so little water? The anomaly left astronomers scratching their heads, and it forced them to consider explanations outside the usual playbook. One possibility is that Atlas formed in a region of its natal star system where carbon dioxide condensed more readily than water. Every young solar system has what scientists call snowlines, boundaries at which different volatile substances can freeze into solids. Close to the star, it's too warm for anything but metals and rock. Farther out, water can freeze, and even farther, carbon monoxide and carbon dioxide solidify. If Atlas originated beyond the CO2 snowline of its home system, its chemistry might naturally favor carbon dioxide over water. But that explanation, while tidy, doesn't fully solve the puzzle. Even in such regions, one would still expect a mixture. Atlas's extreme imbalance suggests something unusual about its formation or its subsequent history. Perhaps radiation from cosmic rays baked its surface for billions of years, sealing away water beneath a crust while leaving CO2 to escape. Or maybe collisions or impacts stripped away water-rich layers, exposing deeper carbon dioxide deposits. Each scenario is possible, but none feels entirely satisfying. There's another oddity, the sheer intensity of its activity at such a distance. Typically, water-driven comets don't wake up until they're closer to the Sun, where heat is strong enough to sublimate ice into vapor. Carbon dioxide, however, turns to gas at lower temperatures, which might explain why Atlas was active so early. Yet, even so, the scale of the emission surprised astronomers. The comet seemed to be exhaling, its coma stretching hundreds of thousands of kilometers like a great cosmic sigh. This raised questions that go beyond chemistry. Was Atlas simply unusual, or was it part of a hidden population of interstellar objects with strange chemistries we've never encountered before? If so, then every interstellar visitor is not just a rock with a tail, but a laboratory, carrying clues about the diversity of planetary systems across the galaxy. Our solar system may be only one recipe among countless variations, and Atlas is a taste of something different. For the average person, chemical ratios might sound dry, like something reserved for lab reports. But think of it this way, it's like finding a fruit you've never tasted before. You expect it to be sweet, like an apple, but instead it's sour or bitter or spiced in ways that don't match anything familiar. That difference alone is enough to tell you it comes from somewhere else, shaped by a different soil, a different climate. Atlas is that alien fruit, and Webb's spectrum is the first bite. There's also a more speculative angle, one that some scientists entertain with caution and others with curiosity. If a comet like Atlas carried an unusual chemical signature, could it be more than a natural fluke? Could the composition itself be a kind of signal? After all, carbon dioxide in such dominance is so rare that it might serve as a marker, a way to stand out against the cosmic background. While the mainstream view is firmly grounded in natural explanations, the idea lingers, if only as a thought experiment. If you wanted to send a message across the galaxy disguised as something ordinary, what better way than through chemistry that looks just a little too strange? Regardless of intent, the implications are significant. If Atlas is natural, then it expands our sense of what's possible in planet formation. It means there are star systems where CO2 dominates over water, places where the balance of ingredients produces worlds unlike any we know. If it's not natural, if it represents something engineered, however unlikely, that possibility would shake the foundations of science. Either way, we are forced to rethink our assumptions. This discovery also connects to an older puzzle. In 2016, another comet, C/2016 R2 Pan-STARRS, displayed unusual chemistry dominated by carbon monoxide and nitrogen compounds. At the time, it was considered an outlier, a curiosity. Now, with Atlas showing even stranger proportions, scientists are beginning to wonder if such anomalies are more common than we thought. Perhaps our solar system is the oddball, with its water-rich comets, while the galaxy at large prefers other recipes. And that leads to a deeper reflection. Comets are not just icy bodies, they are couriers of information. They carry in their makeup the story of their birth environments, the temperatures, pressures, and radiation fields that shaped them. Every deviation from the norm is a clue, a whisper from a place we cannot see directly. To study Atlas is to read a message billions of years old, one encoded not in words but in molecules. Of course, part of the mystery lies in the fleeting nature of the opportunity. Atlas is moving fast, and our time to study it is short. Webb captured its strange chemistry from a distance, but soon it will slip away, taking its secrets with it. We are left with data, spectra, light curves, models, but the comet itself will vanish into the dark. It's a bit like catching a glimpse of a stranger at a crowded station, noticing something remarkable about them, and then watching them disappear before you can ask who they are. Still, that brief glimpse matters. It forces us to question, to wonder, to expand our vision of what the galaxy might contain. In the end, Atlas's hidden chemistry is not just about carbon dioxide or water ratios. It's about humility. It reminds us that our assumptions, our sense of what is normal in space, are based on a very small sample size. With each new interstellar visitor, that sample grows, and our picture of the galaxy becomes richer, stranger, and more complex. Survival in the interstellar void. If you step outside on a cold winter night and look up, it can feel as though the stars are frozen in place, quietly twinkling in a calm and peaceful sky. But space is anything but calm. It is a restless ocean of energy, collisions, radiation, and endless motion. For a fragile body like 3I Atlas, a comet made not of solid iron but of porous ice, dust, and stone, simply existing in that ocean for billions of years is almost beyond belief. How could something so small and so fragile survive a journey so long and so harsh? To answer that, we need to imagine what life is like for an object adrift between the stars. The interstellar void is not empty, but compared to our solar system, it is sparse and desolate. A comet like Atlas spends almost all of its existence in darkness, far from the warmth of any star. Temperatures plummet to just a few degrees above absolute zero, cold enough that atoms barely move. In this frozen silence, Atlas drifts, its molecules locked in place like insects trapped in amber. That deep freeze, paradoxically, is its first line of protection. On Earth, time erodes everything. Wood rots, metal rusts, mountains crumble. But in the interstellar void, time slows. Chemical reactions grind almost to a halt, preserving ices and minerals for billions of years. In a sense, Atlas has been in a kind of cosmic cryogenic state, frozen not just in temperature, but in time itself. It is like a relic kept in a freezer, untouched, unchanged, waiting to be discovered. But cold alone cannot explain survival. The galaxy is not a gentle place. All around, stars explode as supernovae, bathing space in lethal radiation. Cosmic rays, high-energy particles traveling near the speed of light, sweep through the void like invisible bullets. Over billions of years, any exposed surface would be blasted and scarred, its molecules broken apart, its structure weakened. And yet, Atlas endures. Scientists believe this endurance comes from its crust. Even a thin outer layer of dust and rock can act as a protective shield, absorbing the worst of the radiation while preserving the pristine material beneath. Over time, cosmic rays may destroy the outer few feet of the comet, turning ice into inert compounds, but the interior remains untouched, holding chemistry as fresh as the day it formed. It's a bit like the rind of an orange, toughened and dried by exposure, while the inside remains juicy and intact. Atlas may be damaged on the outside, but within it still carries the original blueprint of its home system. Then there are collisions. At first, it might seem impossible for something the size of Atlas to survive billions of years without being shattered. After all, space is full of debris. But here, the emptiness of interstellar space works in its favor. Between stars, the distances are so vast that direct collisions are vanishingly rare. It is the opposite of the crowded asteroid belt in our solar system. Out there, Atlas can drift for millions of years without so much as brushing against a pebble. The void is not safe in every sense. Radiation is constant, but it is roomy. That spaciousness gives a fragile comet the breathing room it needs to endure. Still, survival in the void is not just a matter of avoiding destruction. It is also about resilience. Comets are loosely bound like dirty snowballs. They are porous, fluffy even, more fragile than rock, but also surprisingly adaptable. When struck by small impacts, their structure can absorb the energy like a sponge rather than shattering like glass. When heated slightly by starlight, their volatile ices can sublimate and escape, but the core remains. It is this strange balance of fragility and flexibility that allows them to persist. Atlas has likely lost layers of itself along the way, slowly eroded by radiation and micro-impacts, but enough has survived to remain whole. We might compare it to an heirloom passed down through generations. Over the years, the edges wear down, the surface gathers scratches, maybe a piece breaks away, yet the heart of the object remains, carrying the essence of what it was when it was first made. Atlas is like that, an heirloom of the galaxy, worn and weathered but still intact, still carrying within it the secrets of its birthplace. Isolation, too, plays a role. For billions of years, Atlas has been alone, drifting through vast gulfs of space where no star's gravity could capture it, no planet could smash it, and no solar wind could strip it bare. Its solitude has been its sanctuary. In human terms, it's like a hermit living far from the bustle of cities, untouched by wars and disasters, quietly enduring while the world changes elsewhere. While stars lived and died, while galaxies collided, Atlas remained, silent and invisible, biding its time until chance brought it here. The sheer timescales involved are humbling. Think of Earth's history, 4.5 billion years of continents shifting, oceans rising and falling, species evolving and vanishing. Through all that, Atlas was already drifting, already a wanderer in the galactic dark. When dinosaurs walked the Earth, it was out there. When the first forests grew, it was out there. When Earth itself was still molten and forming, Atlas may already have been on its journey. Its survival is not measured in centuries or millennia, but in epochs so vast that human history barely registers as a blink. And yet, despite its endurance, Atlas is not immortal. Its current passage near our Sun is dangerous. The same heat that reveals its chemistry also threatens to tear it apart. Already, astronomers have noticed that interstellar comets like Atlas are fragile. prone to fragmenting as they warm. Borisov, the second interstellar object ever found, shed dust and debris as it passed the Sun. Atlas, too, may break apart, its billions of years of survival undone in a single close approach. That possibility adds a bittersweet quality to our observations. We may be witnessing both its story and its ending. There is poetry in that, to think that something could endure so long, travelling untold distances in silence, only to disintegrate in the light of our sun. It feels like a reminder of how fragile endurance truly is. Survival in the void is one thing, survival in the presence of a star is another. Stars give life, but they also destroy. Atlas may be learning that lesson now, just as our instruments watch. But regardless of what happens, the fact of its endurance until now is a marvel. It shows us that the galaxy is not just a place of violence, but also of persistence. That even fragile things can last if given enough space, enough solitude, and just the right balance of protection and chance. Atlas is proof that survival is not always about strength. Sometimes it is about patience, about drifting quietly in the margins until the moment of discovery, a relic of an older galaxy. When we look up at the night sky, the Milky Way stretches across it like a shimmering river of stars, calm and familiar, as if it has always been this way. But our galaxy, like everything else in the universe, has a past, a turbulent, chaotic youth filled with collisions, mergers, and violent outbursts of star formation. To suggest that 3I Atlas may be a relic from that time is to suggest that we are looking not merely at a comet, but at a fossil from an era when the galaxy itself was still trying to find its shape. Astronomers estimate that the Milky Way is more than 13 billion years old. In its early days, it was not the orderly spiral we see today, but a rough and tumble collection of smaller galaxies merging together, stars being born in furious bursts and colossal explosions scattering elements across the void. If Atlas really dates back to those times, it carries within it a record of conditions that no telescope could ever show us directly. It would be, quite literally, a messenger from a younger galaxy. The idea might sound extreme at first. After all, comets are fragile, loose conglomerations of ice, dust and stone. How could such a delicate body survive billions of years intact? Yet, as we explored earlier, survival in the interstellar void is possible. If a comet was formed, buried in the far reaches of a planetary system, and later ejected into the vast empty stretches between stars, it could spend eons drifting undisturbed, its chemistry preserved in the deep freeze of space. Atlas could be one such body, a time capsule flung outward when the Milky Way was still in its adolescence. One clue lies in its unusual chemistry. When the James Webb Space Telescope studied Atlas, it revealed a dominance of carbon dioxide unlike anything we normally see in comets of our solar system. This strange imbalance could hint at formation conditions very different from those that shaped our own planets and comets. If Atlas condensed from material in an early chaotic star system, perhaps one with a different balance of volatiles, it might explain its bizarre composition. In other words, Atlas may not simply be foreign in space, but also in time, carrying a recipe that belongs to a galactic kitchen long gone. To put this in perspective, imagine finding an ancient seashell on a mountain. Its ridges and patterns tell you not just about the creature that made it, but about the ocean that once covered that land. In the same way, Atlas tells us about the environment in which it formed, a world that may no longer exist, orbiting a star that could itself be long dead. Perhaps its parent star exploded as a supernova, scattering its worlds and flinging Atlas into exile. Or perhaps it was stripped away during a galactic merger, when two star systems collided and debris was hurled outward like sparks from a fire. The Milky Way's youth was full of such events. Entire dwarf galaxies were swallowed, Black holes fed greedily, blasting jets of energy into the interstellar medium. Star clusters were torn apart, their contents scattered across the growing spiral. In such chaos, countless comets and asteroids must have been ejected, set adrift into interstellar space. Atlas could be one of those ancient wanderers, still carrying the fingerprint of that violent era. It's humbling to think that something so small could preserve a memory of something so vast. On Earth, we look to fossils, bones and stones to reconstruct the past. In space, we look to comets. They are the fossils of planetary systems, the bones of creation itself. And if Atlas truly dates back to the Milky Way's youth, it might be the oldest artifact humanity has ever encountered. Older than Earth, older than the Sun, older even than many of the stars that make up the familiar constellations above us. There's a kind of poetry in this idea. We tend to think of history in terms of human time, centuries, millennia, perhaps a few tens of thousands of years. Atlas stretches that perspective to billions. It suggests that while civilizations rise and fall, while species evolve and vanish, while continents drift and seas shift, some things simply endure. A fragile body of ice and dust drifting through the darkness, untouched by any hand, older than memory itself. But there's also a mystery here. If Atlas is truly that old, then it is more than a comet. It is an ambassador of deep time. It has seen things we can only imagine, the galaxy when it was half its current size, the birth of stars that have since gone cold, the collisions of galaxies that reshaped the Milky Way into its present form. Of course, the comet itself cannot remember these things, but its very existence, its chemistry, its survival, is testimony to that forgotten age. For the average person, it might help to think of Atlas as a kind of ancient coin. Imagine picking up a weathered piece of metal from the ground, only to learn it was minted thousands of years ago in a civilization long gone. The coin itself is small, ordinary even, but it holds within it the imprint of another world. Atlas is like that, ordinary in shape, just another icy body, but carrying an imprint of conditions that predate not just our history, but our very planet. Some astronomers even speculate that interstellar comets like Atlas could serve as tools for cosmic archaeology. By studying their makeup, we can reconstruct the environments of long-vanished star systems, just as archaeologists piece together lost cultures from pottery shards. In that sense, Atlas is not just a comet, it is a relic, a fragment of a story we could never otherwise know. And perhaps that is why people feel such awe when contemplating it. Not because it is large, it is not. Not because it will strike Earth, it will not. But because it carries with it the weight of time itself. It is the embodiment of survival, of endurance, of connection across billions of years. To watch it drift past is to touch, however briefly, the deep history of the galaxy we call home. Atlas will not stay. Its hyperbolic orbit ensures it will leave us soon, vanishing into the black as it continues its endless journey. But for now, as it glows faintly in the night sky, it invites us to look not just outward, but backward. To imagine a galaxy still in its youth, stars being born in violent clusters, planets forming and colliding, and among it all, a comet taking shape. A comet that, against all odds, has survived to be seen by us today. In that light, Atlas is more than a traveller. It is a relic of an older galaxy, a whisper from the past, a reminder that the universe is ancient and that we, fleeting as we are, have the rare privilege of witnessing something that has endured since before our world even began. Comparing Oumuamua and Atlas. In October of 2017, a strange object swept through the solar system and immediately caught the world's attention. It was named Oumuamua, a Hawaiian word meaning scout or messenger from afar, and it was unlike anything astronomers had ever seen. For weeks, it dominated headlines. Was it a comet, an asteroid, or could it, some dared to whisper, be something artificial? The fascination was so intense that even people who rarely thought about space suddenly found themselves pondering the mysteries of the stars. Oumuamua was strange not only because it was the first confirmed interstellar object ever observed, but also because of how it behaved. Unlike typical comets, it showed no obvious tail. Instead, it appeared as a thin, elongated shape tumbling through space, reflecting sunlight in ways that made its dimensions difficult to pin down. Some thought it looked like a cigar, others suggested it might be as flat as a pancake. To make matters even more puzzling, its trajectory shifted ever so slightly, as though it were being pushed by something invisible. Normally, comets are nudged by jets of gas as they release material, but no such jets were seen. The mystery gave rise to speculation, including the bold idea that Oumuamua could be a kind of alien probe or solar sail. But just a few years later, in 2019, another interstellar visitor appeared, this time one more in line with expectations. 2I/Borisov, discovered by amateur astronomer Gennady Borisov, looked and acted like a classic comet. It had a fuzzy coma, a long tail, and a chemistry similar to the comets we know in our solar system. Borisov reassured scientists that interstellar comets were real and not all as bizarre as Oumuamua. Then came 3I Atlas. At first, it might have seemed like Borisov's sibling, another comet, this time caught by modern surveys before it could slip away unnoticed. But as data began to come in, Atlas started to reveal qualities that placed it in a category all its own. If Oumuamua was strange for its shape and motion, Atlas is strange for its speed, its chemistry, and the very questions it raises about the galaxy's hidden population of wanderers. One of the key differences lies in their visibility. Oumuamua was faint, barely large enough to detect, and by the time we saw it, it was already leaving. We had only weeks to study it, and no telescope could get a detailed look. It was like spotting a bird out of the corner of your eye as it flies past. You catch a glimpse, but you never really see the whole thing. Atlas, by contrast, has given us more time. Its activity, driven not by water but by carbon dioxide, made it brighter and more noticeable. Telescopes, including the James Webb Space Telescope, have been able to gather detailed spectra of its composition. Instead of a fleeting shadow, Atlas is more like a guest, lingering just long enough for us to ask a few questions, though it too will eventually vanish forever. The chemistry of Atlas may be its most unsettling trait. Oumuamua puzzled astronomers with its lack of a visible tail, but Atlas goes further, showing a chemical dominance of carbon dioxide that defies expectations. In our solar system, water is the star of the show in cometary outgassing, with CO2 playing a secondary role. Atlas reverses this balance, releasing carbon dioxide in overwhelming quantities compared to water. It's as if the comet itself belongs to a different category of creation, formed under conditions alien to anything we know. And then there's the matter of speed. Oumuamua travelled quickly enough to prove its interstellar nature, but Atlas moves faster still, so fast that its hyperbolic trajectory leaves no doubt it came from far beyond. Its velocity suggests a violent ejection, perhaps from a system more chaotic than our own, or a history of close encounters with giant planets and stars that slingshotted it into permanent exile. If Oumuamua was a scout, then Atlas is a runaway, a comet that seems almost too eager to escape the galaxy's grasp. For the public, Oumuamua sparked imagination in a way few astronomical discoveries do. Its name became a cultural reference point, appearing in novels, news articles, and speculative debates. Atlas, meanwhile, has been quieter in the headlines, but in many ways it poses deeper questions. If Oumuamua was an outlier, a freak occurrence, Atlas suggests it is not alone. There may be countless such wanderers, each with their own strange chemistries and trajectories, drifting unseen through interstellar space. That realization is both thrilling and unsettling. Thrilling because it means the universe is richer than we imagined, filled with relics of alien star systems waiting to be discovered. Unsettling because it forces us to confront just how little we know. Oumuamua showed us that interstellar visitors exist. Borisov reassured us they can look familiar, but Atlas reminds us they can also be profoundly strange, carrying signatures that don't match any of our expectations. It's worth noting, too, the psychological difference between them. Oumuamua felt eerie because of what we couldn't see, its missing tail, its odd acceleration. It was the silence of the object that made people wonder if it was artificial. Atlas, on the other hand, feels unsettling because of what we can see. Its chemistry is in plain view, and yet it refuses to make sense. It is as though nature itself is whispering in a language we don't yet understand. Perhaps the best way to think of it is this: Oumuamua was a question mark. Atlas is an exclamation point. The first left us wondering whether interstellar objects might be out there. The second tells us they definitely are, and that they may be far stranger than we dared to imagine. And as Atlas drifts away, leaving us with data and unanswered questions, it invites us to consider what else might be coming. If the first three interstellar visitors were this diverse, Oumuamua mysterious, Borisov familiar, Atlas bizarre, what will the fourth look like? A shard of a shattered planet? A comet with exotic ices we've never seen? Or something so unusual it forces us to rewrite the textbooks yet again? Whatever comes next, Atlas ensures that we'll be paying attention. Its strangeness reminds us that the galaxy is full of travelers, each with its own story. And in comparing Oumuamua and Atlas, we are not just comparing two comets. We are glimpsing the vast diversity of worlds beyond our own, each one a reminder that the universe is stranger, older, and more unpredictable than we can possibly imagine. Comets as cosmic archives. When archaeologists dig into the Earth, they sometimes find objects that look unremarkable at first glance. Fragments of pottery, stone tools, a piece of carved bone. Yet these objects are priceless, not because of their beauty, but because of what they preserve, a glimpse into the world of the past. Comets serve a similar role in astronomy. They are the universe's archives, frozen time capsules that preserve the earliest conditions of the systems where they were born. And in the case of 3i Atlas, that archive does not belong to us. It belongs to another star system, perhaps one long vanished, and it drifts into our skies as a messenger from that alien history. To understand why comets are such powerful archives, we need to think about how they form. When a star is young, it is surrounded by a swirling disk of gas and dust, a nursery of planets, moons, and smaller bodies. In these outer regions, far from the warmth of the star, ices condense: water, carbon dioxide, methane, ammonia. Mixed with dust and rocky material, they clump together into fragile bodies no bigger than mountains. These are the comets, the leftover building blocks that never grew into planets. What makes them special is that they remain largely unchanged. Unlike planets which undergo volcanism, tectonics, atmospheres and erosion, comets stay locked in deep freeze. Their interiors are so cold and inert that the chemistry inside them has barely altered since the moment of their birth. It's as if nature tucked them away in a freezer and forgot about them for billions of years. When we study them, we are looking at untouched samples of the conditions that existed at the dawn of a solar system. Our own solar system provides an excellent example. Missions like ESA's Rosetta, which studied comet 67P/Churyumov-Gerasimenko, revealed organic compounds, ingredients that may have played a role in seeding Earth with the raw materials for life. These comets are not just leftovers, they are witnesses, preserving details of the chemical environment that gave rise to planets, atmospheres, and perhaps life itself. Now imagine what an interstellar comet like Atlas represents. Instead of carrying the story of our sun's birth, it carries the story of another star. Every molecule frozen inside it is a word in a language we have never read before, describing the conditions of a system we cannot visit. Was its parent star hotter or cooler than the sun? Was the disk around it rich in carbon, poor in oxygen, or flooded with exotic compounds rare in our neighborhood? Each ratio of gases, each trace of ice, each mineral grain holds clues. This is why the James Webb Space Telescope's findings about Atlas are so profound. Its overwhelming carbon dioxide dominance tells us its archive is different from ours. If we think of our solar system's comets as books written in a familiar script, Atlas is a book in a foreign tongue. The letters are recognizable. We know what carbon dioxide is, what water ice is, but the story they tell does not match the one we know. That difference expands our understanding of what is possible in planetary formation. In human terms, it's like uncovering a library buried under volcanic ash. The books are still there, the ink preserved, and as you open them, you realize the stories describe a culture unlike anything you've seen. Their myths, their food, their language, everything is strange yet fascinating. Atlas is that kind of discovery. A library preserved in ice, drifting across the galaxy, landing briefly in our field of vision. Another important aspect of comets as archives is their portability. Unlike planets, which remain fixed around their stars, comets can be ejected. A brush with a giant planet, a collision, or the gravitational tug of a passing star can fling them into interstellar space. Once free, they drift indefinitely, carrying their frozen archives across the galaxy. In this way, comets become couriers of information, not just archives of their home systems, but ambassadors carrying pieces of alien chemistry to other stars. There's even speculation that comets could play a role in panspermia, the idea that the building blocks of life, or life itself, could be transferred between star systems on icy bodies. If so, then comets are not just archives of chemistry, but carriers of potential. They may hold the seeds of life, preserved in their cold interiors, waiting to be delivered. Whether or not that is true, their role as preservers of history is undeniable. The fragility of this preservation makes them even more precious. When comets approach stars, they release their contents in spectacular displays of tails and comas, but in doing so, they also erode. Over time, repeated passages can strip away their archives until little remains. Interstellar comets like Atlas, however, are often making their first and only close approach to a star in billions of years. That means the record inside them could be nearly pristine, unspoiled by repeated heating. There's a poignant contrast here. On Earth, archives are often buried to protect them, scrolls hidden in caves, artifacts sealed in tombs, documents kept in vaults. In space, the archives are scattered, drifting through the dark. They are not guarded, but exposed, waiting for the rare moment when they cross paths with a civilization capable of reading them. We are that civilization now, at least for Atlas, and it is humbling to realize that we almost missed it. Oumuamua passed too quickly for us to study in detail. Borisov gave us a better glimpse, but Atlas, bright, active, and chemically strange, has opened its archive more fully. Through telescopes, we can read a little of its story, though we may never know it all. And when it leaves, the archive will go with it, vanishing into interstellar space, perhaps never to be opened again. That transience makes the study of comets feel urgent, even poetic. Each one is a chapter of galactic history carried across impossible distances, offered to us for only a fleeting time. They remind us that the universe is not static, that histories overlap and intersect, that our story is bound up in countless others. To look at Atlas is to glimpse the frozen past of a world we cannot see, a world that may no longer exist. And so, comets are more than icy rocks. They are the archivists of the cosmos, each one a preserved record of creation. To encounter them is to open a time capsule, to touch the beginnings of other stars and other worlds. Atlas, with its strange chemistry and fleeting visit, reminds us that the galaxy is full of such archives waiting to be read. And in its quiet glow, drifting through our skies, we are invited to remember that the universe, too, keeps its own memory, written not in books or stone, but in ice and dust that endure for billions of years. The curse of observation. Windows. In astronomy, timing is everything. We imagine the universe as constant and eternal, stars burning steadily while planets circle in quiet repetition. Yet when it comes to rare visitors like Three-Eye Atlas, our chance to watch them is governed not only by their fleeting presence, but also by where they appear in the sky. For astronomers, this limitation has a name they use half jokingly, half in frustration: the curse of observation windows. It means that even as Atlas reveals its most exciting secrets, its strange chemistry, its unusual behavior, it drifts into a position where our telescopes can no longer see it. And, as fate would have it, this often happens at the worst possible moment, just as the comet grows most active, just as the data becomes most valuable. Instead of basking in continuous observation, we are forced to watch the curtains close. In the case of Atlas, the problem is its orbit relative to Earth and the Sun. As it swung inward, the comet became brighter, releasing carbon dioxide in great plumes, making its coma glow. This should have been the moment of richest discovery, a treasure trove of chemical information waiting to be collected. But as it brightened, its apparent path carried it closer and closer to the Sun's glare. From Earth, the comet slipped into daylight, its faint light drowned in solar brilliance. Telescopes that once tracked it easily had to give up, forced to wait until it emerged again, if it did at all, on the far side of the Sun. For astronomers, this feels like being handed a rare manuscript only to have someone slam it shut halfway through the reading. You know there are secrets inside, but the timing of the universe itself has robbed you of the chance to see them. That sense of frustration has long accompanied comet hunters, who must work with narrow windows of opportunity before their quarry vanishes behind the sun or slips back into darkness. But for the public, such disappearances often take on a more dramatic flavour. Whenever a rare object like Atlas disappears into the sun's glare, speculation flourishes. What is it doing while we cannot see it? Is it breaking apart? Is it changing course? Could something be hidden there? These questions are not only natural, but also deeply human. We are uncomfortable with gaps in our knowledge, and our imaginations rush to fill them. History provides plenty of examples. In the 1990s, Comet Hale-Bopp's long visibility and its temporary disappearance led to a wave of speculation, including conspiracy theories about spacecraft hiding in its tail. In more recent years, comets lost behind the sun have fueled internet rumors of impending catastrophe, despite no scientific evidence to support such fears. Atlas, as a confirmed interstellar visitor, adds an extra layer of intrigue. Its foreign origins make its temporary invisibility feel even more suspicious to those inclined toward cosmic paranoia. Even without sensationalism, the scientific uncertainty can be unsettling. Imagine watching a delicate vase wobbling on a shelf, ready to fall. You want to keep your eyes on it, to know if it shatters. But just before the crucial moment, someone draws a curtain and you are left to wonder, did it fall? Did it survive? That is what it feels like to study a comet that disappears into the sun's glare. Astronomers know it may fragment, as many comets do, but they cannot confirm until it emerges again, if it emerges at all. The curse of observation windows also reflects a deeper truth about astronomy. Our perspective is limited. We live on a small planet, orbiting one star, with telescopes fixed on Earth's surface or placed in near-Earth orbit. We cannot move to other vantage points at will. If the sun blocks our view, we must wait. That helplessness can be frustrating, but it is also part of the beauty of astronomy, the recognition that we are not in control, that the universe reveals itself only on its own terms. For Atlas, this disappearance behind the sun came just as its activity was spiking, just as Webb and ground-based observatories were gathering their most tantalizing data. Scientists could model what was happening, extrapolating from what they had seen, but they could not watch directly. It was a reminder that even in the age of powerful telescopes and constant surveillance, the cosmos still keeps its secrets. And perhaps that is why these gaps fuel the imagination so strongly. In the absence of observation, possibility blooms. What if Atlas is not what it seems? What if its chemistry is part of a larger pattern we cannot yet see? What if something unexpected is revealed when it re-emerges? These questions linger in the silence, keeping the story alive long after the comet itself has slipped from view. In the end, the curse of observation windows is not just a limitation, but a kind of narrative tension. It leaves us with cliffhangers, moments of uncertainty where imagination takes over. Will Atlas survive its passage? Will it fragment? Will it return stranger than before? We cannot know until the curtain lifts again. For those watching from Earth, it is a reminder that astronomy is as much about patience as discovery. Sometimes the universe offers a glimpse and then withholds the rest, forcing us to wait, and while we wait, we speculate, we wonder, and we imagine. In that sense, the curse of observation windows is also a gift. It keeps mystery alive, fueling curiosity and awe, reminding us that the cosmos is not a book we can flip through at will, but a story that reveals itself page by page in its own time. The global hunt. When an interstellar comet like 3I Atlas enters the solar system, the moment is fleeting. Such objects move at extraordinary speeds, and their visits last only a short while before they disappear into the depths of space, never to return. For astronomers, that urgency creates a rare kind of global excitement, a call to action, a hunt that stretches across continents and time zones as observatories race to capture every possible detail before the opportunity is gone. The discovery of Atlas began like many astronomical finds, as a faint speck of light detected by a survey telescope. At first it seemed unremarkable, a new comet, dim and distant, one of dozens spotted each year. But as astronomers calculated its orbit, the truth emerged. This was no ordinary comet. Its trajectory was hyperbolic, meaning it was not bound to the sun. It was an interstellar visitor, only the third ever confirmed. Instantly, that realization triggered a cascade of phone calls, emails, and urgent proposals to telescope committees around the world. Everyone wanted to take part in observing it. Large observatories with powerful instruments adjusted their schedules, sometimes cancelling planned programs to make room for Atlas. Time on major telescopes is among the most valuable resources in astronomy. Weeks or months of proposals often compete for a handful of nights. Yet Atlas leapt to the front of the line. Its rarity demanded attention. From Chile's Atacama Desert to Hawaii's Mauna Kea, from the Canary Islands to space-based observatories orbiting Earth, scientists coordinated their efforts, each facility offering a piece of the puzzle. This global hunt was not only about professional astronomers. Amateur observers also joined in, setting up backyard telescopes and sharing their images online. Comet chasers are a passionate community, and many take pride in contributing data to the scientific record. For Atlas, their observations helped fill in the gaps between large observatory sessions, offering a continuous record of its brightness and behavior. In a sense, The comet united two worlds, the cutting edge of billion-dollar observatories and the dedication of individuals with modest equipment but limitless curiosity. One of the most fascinating aspects of this hunt was the coordination it required. Because Earth rotates, no single observatory can watch the comet continuously. But by handing off observations from one location to another, Hawaii to Europe to South America to space-based instruments, astronomers stitched together a nearly unbroken record of Atlas's activity. It was like a relay race, with each observatory carrying the baton for a few hours before passing it along. This global coverage allowed scientists to track subtle changes, outbursts of gas, shifts in brightness, and the slow evolution of the comet's coma and tail. The James Webb Space Telescope played a starring role, peering into Atlas's composition with its unmatched sensitivity to infrared light. But Webb alone could not tell the whole story. Ground-based telescopes added details about dust, plasma, and the shape of its orbit. Solar observatories designed to study the Sun contributed when the comet moved into their fields of view. Even spacecraft not originally intended for comet hunting were drafted into service, their instruments repurposed to capture data. It was a moment of scientific improvisation, with researchers using whatever tools were at hand to glimpse this cosmic wanderer. There is something profoundly human about this global hunt. In a world often divided by politics, borders, and rivalries, a comet can inspire unity. Scientists in different countries, speaking different languages, set aside other concerns to work together, bound by a shared desire to understand. For a brief moment, Atlas was not just a comet, it was a common goal, a symbol of collaboration across the planet. This sense of urgency and teamwork has precedent. When Oumuamua was discovered in 2017, the global community responded with similar speed, though its faintness limited what could be learned. With Borisov in 2019, the rush to observe was intense, but tempered by its more familiar, comet-like behavior. Atlas, however, combined the urgency of rarity with the shock of strangeness. Its bizarre chemistry made it irresistible, and every observatory wanted to contribute. The result was a dataset far richer than anything possible from one location alone. For the general public, the idea of telescopes racing to capture a comet might sound abstract, but it helps to think of it like chasing a storm. Meteorologists track hurricanes with radar, satellites, and ground sensors, each tool providing a different perspective. A single radar station cannot see the whole storm, but together they create a complete picture. The hunt for Atlas was like that, a storm in space, visible only for a short while, demanding rapid coordination to catch every angle before it passed. And then, just as the observations grew most exciting, came the frustration of the sun's glare. Atlas slipped into a region of the sky where even the most powerful Earth-based telescopes could not see it, hidden behind the blinding light of our star. It was a cruel twist of timing, the comet most active just as it became most invisible. Yet the global hunt did not end there. Some observatories waited for it to emerge again, while others turned to spacecraft beyond Earth's atmosphere to continue the chase. Even in absence, the network of astronomers stayed connected, ready to resume the pursuit the moment it returned to view. The story of Atlas is not only the story of a comet, it is also the story of human determination to glimpse the fleeting, to preserve knowledge before it slips away. Just as ancient hunters tracked animals across landscapes, modern scientists track cosmic wanderers across the sky. The quarry is different, but the spirit is the same, a mix of patience, persistence, and awe. In the end, the global hunt for Atlas shows us something essential about our relationship with the cosmos. We may be small, tethered to one planet, limited by narrow windows of observation, But when the universe offers us a rare gift, we respond with everything we have: telescopes, satellites, communities, and the combined effort of a world looking upward together. And in that effort, we not only learn about the comet, we learn something about ourselves, that in the face of mystery, curiosity unites us, turning the whole Earth into a single observatory, watching the heavens as one. NASA's careful language. Whenever a rare object like 3I Atlas streaks through our skies, the scientific excitement is accompanied by another kind of tension: the public's concern. People naturally wonder, what does this mean for Earth? Could it hit us? Could it disrupt our lives? And in those moments, all eyes turn to NASA and other space agencies for answers. Their statements are always clear, always reassuring, and always cautious. This careful language is no accident. NASA and its partners know that a single phrase, misinterpreted, can ignite waves of panic or wild speculation. If you look closely at their press releases and official updates, you'll notice the pattern. They emphasize distance, they stress the lack of threat, and they frame discoveries in a calm, measured tone. When Atlas was confirmed as interstellar, NASA was quick to note that it posed no danger to Earth and that its path was purely a scientific opportunity. But why this caution? On one hand, it's simply good communication. Astronomers live in a world of nuance and uncertainty, but the public often craves definitive answers. A small statistical risk, even 1 in a billion, can sound terrifying when described out of context. By choosing words that soothe rather than alarm, agencies try to prevent unnecessary fear. After all, the chances of any interstellar comet striking Earth are effectively zero. Yet on the other hand, this careful language feeds curiosity and sometimes paranoia. Whenever an official body reassures too firmly, some people begin to wonder, what are they not telling us? Why emphasize safety so strongly unless there was ever a reason to doubt it? This suspicion is amplified by history. Over the decades, governments have occasionally withheld information, not always maliciously, but often to avoid panic. The memory of such secrecy lingers, shaping how the public reads every line. Consider Oumuamua in 2017. Its odd acceleration sparked debates even among professional astronomers, with some openly entertaining the possibility of artificial origins. NASA remained cautious, sticking to safe language. Natural explanations were more likely, more observations were needed, and no evidence pointed to aliens. They never ruled out speculation entirely, but their phrasing avoided extremes. The goal was to maintain credibility without fueling hysteria. With Atlas, the pattern repeated. As soon as Webb detected its unusual carbon dioxide dominance, the language was carefully neutral. Unexpected, unlike typical comets, may point to different formation conditions. These phrases invite curiosity but avoid sensationalism. What NASA did not say is just as interesting as what it did. They did not speculate publicly on whether such chemistry implied exotic origins. They did not suggest catastrophic scenarios. Instead, they let the facts stand, restrained and unembellished. For those who read between the lines, this restraint can feel unsatisfying. People crave drama, story, even a hint of danger. When agencies refuse to give it, imagination rushes in to fill the gap. Some picture hidden risks, fragments breaking off unseen, new paths calculated but not revealed. Others imagine more extraordinary secrets, alien technology, signals, or cover-ups. In truth, the reality is usually far less dramatic. Scientists speak carefully because they must. Their credibility depends on precision. A dramatic claim, later disproven, can erode public trust for years. But there is another, subtler reason for careful language: wonder itself. Scientists understand that not every discovery needs danger to be meaningful. Atlas is fascinating not because it threatens us, but because it exists, because it carries chemistry from another system, because it moves faster than any comet we've seen, because it is a messenger from beyond. If every announcement were framed in terms of doom, we would lose sight of that deeper beauty. Still, the balance is delicate. Too much reassurance and the public grows suspicious. Too little, and panic takes hold. The curse of modern communication is that silence can be as dangerous as exaggeration. NASA and other agencies walk that line with care, knowing that their words ripple far beyond the scientific community. Think of it this way: when a doctor delivers a diagnosis, they choose their words carefully. They want to convey truth without overwhelming the patient. They avoid speculation until evidence is clear. They stress what can be done, not just what is uncertain. NASA operates in much the same way. Their careful language is not deception. It is a kind of bedside manner for the planet. And yet, as Atlas vanishes into the sun's glare and re-emerges changed, or perhaps fragmented, one cannot help but feel the tension between what is said and what is left unsaid. The public will always wonder if there is more beneath the surface, if the neat press releases mask a deeper unease. In that sense, NASA's careful words achieve both their goal and their paradox. They calm us, but they also remind us that the universe is full of mysteries too vast, too strange, to ever be wrapped neatly in language. Perhaps that is the point. The cosmos is not a press release. It is a story still unfolding. And while space agencies may choose careful phrasing, the comet itself speaks more freely, glowing faintly in our skies, carrying questions we cannot yet answer. Atlas does not reassure or withhold. It simply is. And maybe, in the quiet between NASA's words, that is the most unsettling truth of all. Are comets perfect disguises? On a quiet evening, if you step outside and look up, the night sky feels serene, stars twinkling like distant campfires, planets glowing steadily, and every so often, a comet drifting past like a ghostly traveller. To us, comets are familiar, even comforting. They have tails of ice and dust, long orbits, and names we remember from history: Halley's, Hale-Bopp, Shoemaker-Levy 9. They fit into the story of the solar system as natural leftovers, frozen relics of creation. But what if that familiarity is precisely what makes them the perfect disguise? When scientists first saw Oumuamua, one of the first interstellar visitors, they struggled to categorize it. Was it an asteroid, a comet? Neither seemed to fit. It had no visible tail, yet it accelerated as though it were venting gases. Its shape was elongated and strange. This led some astronomers, serious ones, not just science fiction writers, to entertain a radical idea. Perhaps it was artificial. Perhaps it was a probe designed to look like nothing more than an ordinary rock drifting through space. That idea has lingered in the back of people's minds ever since. And now, with 3i Atlas showing chemistry unlike any comet we know, the question arises again: could comets be the perfect camouflage for machines, scouts, or artifacts launched by civilizations long gone? From a practical perspective, the disguise is brilliant. Comets are expected in every star system. They form naturally in the icy outer regions, billions of miles from their suns. They wander, they collide, they get flung out into interstellar space. If you were an advanced species wanting to send probes across the galaxy, why not wrap them in cometary material? The ice would act as a shield against radiation. The dust and rock would protect delicate machinery. And from a distance, even to advanced telescopes, the object would look completely natural. Imagine a probe nestled inside, powered down, waiting. For millions, perhaps billions of years, it drifts. To any observer, it is nothing more than a comet. But if it passes close to a star, perhaps it wakes, collects data, transmits a signal, or simply continues on its path, blending back into the sea of debris. the perfect spy hidden in plain sight. This may sound like science fiction, and in truth it is speculation, yet it's speculation rooted in reason. Human engineers already think along similar lines. When we send spacecraft into deep space, we coat them with shielding to protect against cosmic rays. We hide instruments inside protective shells. If we had the technology, disguising a probe as a natural object would make perfect sense, especially in a universe where contact with another civilization might not always be safe. Philosophers of space exploration sometimes call this the dark forest idea, after the notion that civilizations may hide themselves in fear of predators. If that is true, then sending a probe disguised as a comet would be one of the safest ways to explore without revealing yourself. A civilization curious about others could scatter millions of such probes across the galaxy, each wrapped in ice, each passing as just another fragment of creation. The unsettling part is that if such probes exist, we would almost never know. Our default assumption is that comets are natural, because all the comets we've studied in detail so far appear to be. Even Atlas, with its strange chemistry, still fits broadly into the cometary family. To prove that one is artificial would require unmistakable evidence, geometry that could not occur naturally, signals of deliberate activity, materials alien to astrophysical processes. And yet, if the disguise is perfect, such evidence might never appear. There's another angle to consider. Comets carry archives, as we discussed earlier. Their ices preserve the conditions of their birth systems. But what if some comets carry more than just frozen chemistry? What if an ancient civilization, long extinct, left behind artifacts deliberately sealed in comets as a way to outlast themselves? Not probes in the sense of machines, but messages, time capsules meant to travel the galaxy. From that perspective, even if Atlas is entirely natural, the idea of comets as carriers of meaning is not so far-fetched. For the public, the suggestion that a comet might be artificial strikes a powerful chord. It blurs the line between science and myth, between astronomy and imagination. Humans have always looked at comets with mixed feelings: awe, fear, reverence. In ancient times, they were omens, symbols of change, harbingers of disaster. Today, they are seen as archives of creation, potential bringers of life through water and organics. To add possible probe to that list is to deepen their mystery, to give them a role not just in natural history, but in cosmic storytelling. Scientists, of course, remain cautious. They know the odds of any given comet being artificial are vanishingly small. Nature is fully capable of producing strange shapes, odd trajectories, and unusual chemistries. And yet, even among scientists, the possibility is not dismissed outright. Avi Loeb, a Harvard astrophysicist, famously argued that Oumuamua might be artificial, sparking debate that continues to this day. For many, the lesson was not that Oumuamua was a probe, but that we should take such possibilities seriously, however unlikely, and design ways to test them. If nothing else, the idea forces us to sharpen our tools. It challenges us to look more closely, to analyze light more carefully, to build telescopes capable of distinguishing between ice and alloy, between dust and design. Even if every comet turns out to be natural, the effort enriches our science, and if one day, just one, turns out to be otherwise, well, that would change everything. Atlas, with its carbon dioxide dominance and strange speed, is almost certainly natural. Yet it feeds this speculation precisely because it is unfamiliar. Its strangeness opens the door to wonder, and wonder is the first step toward both science and imagination. Whether or not comets are truly disguises, they remind us of how much we do not know, how much remains hidden in the vastness of space. Perhaps that is the true disguise, the universe itself, cloaked in mystery, revealing only what we are ready to see. And in that darkness, each comet, Whether an icy relic or something more becomes a question mark glowing softly in the night, daring us to look closer. Machines that outlast civilizations. The thought of building a machine that endures for billions of years feels almost absurd. On Earth, our greatest works rarely survive more than a few thousand. The pyramids stand as icons of longevity, yet they are mere infants compared to cosmic timescales. Even the most carefully engineered spacecraft we've launched, the Voyagers, the Pioneers, are expected to endure, at best, a handful of millions of years before radiation, collisions, and entropy reduce them to dust. And yet, when we look at the possibility of interstellar probes disguised as comets, or relics like 3I Atlas carrying traces of alien design, we are forced to wonder, what kind of technology could truly outlast civilizations? To begin answering that, it helps to reflect on the fragility of human creations. Consider a smartphone, sleek, powerful, packed with knowledge, yet within a decade, its battery swells, its screen cracks, its software becomes obsolete. Cars rust away in decades, buildings collapse within centuries if not maintained. Even stone monuments are slowly eaten by wind, rain, and time. By comparison, Earth itself feels eternal, yet even continents drift, mountains crumble, and oceans shift over millions of years. On human scales, permanence is an illusion, but space is a different arena, a place of silence, of deep cold, of near emptiness. In the right conditions, things can last far longer than they would on Earth. A machine placed far from stars, shielded by ice or rock, could drift for aeons, untouched by weather or biology. This is where the idea of comet-like probes becomes compelling. An object wrapped in protective layers, dormant until it nears a star, might last longer than the civilization that built it. What would such a machine require? First, durability. Materials must resist radiation, micrometeoroids, and the slow but relentless degradation caused by cosmic rays. On Earth, metals corrode and plastics decay. In space, the enemy is atomic breakdown, high-energy particles slamming into molecular bonds. Advanced civilizations might develop alloys or composites that self-heal, or crystalline structures stable over cosmic time. Perhaps even materials that we cannot yet imagine, engineered at the atomic level to resist entropy. Second, simplicity. The more complex a system, the more points of failure. A truly eternal machine might not be sleek or sophisticated, but rugged and minimal. Think of stone tools compared to modern electronics. One shatters, the other corrodes, but a chipped flint can still cut after 1,000,000 years. Likewise, an alien probe built for endurance might emphasize reliability over elegance, redundant systems, simple functions, mechanisms designed to withstand rather than dazzle. Third, dormancy. A machine running continuously for billions of years is doomed. Energy sources degrade, parts wear out. But if it can sleep, waking only when triggered by the warmth of a star, the tug of gravity, the touch of light, it could conserve itself. Like a seed locked in permafrost, waiting for spring, it might remain dormant for eons until conditions awaken it. This is not science fiction alone. We have glimpses of it already. Our own spacecraft, like Voyager 1 and Voyager 2, are now in interstellar space, powered by the slow decay of plutonium. Their instruments are shutting down one by one to conserve energy, but even as dead hulks, they will drift for hundreds of millions of years. They will not operate forever, but their shells, gold-plated records, antennae, circuitry, may outlast humanity itself. To a distant observer, they will look like tumbling, inert rocks. What if an advanced civilization took this idea further? Imagine a probe encased in kilometers of ice, camouflaged as a comet. Its outer layers protect the delicate core, while cosmic radiation slowly alters only the surface. Inside, a dormant system waits, perhaps for a signal, perhaps simply for chance discovery. Such a probe could cross galaxies, surviving long after its makers vanished, carrying a silent message from a forgotten world. In some ways, nature itself gives us examples of machines that outlast civilizations, comets, and asteroids. These objects endure not because they are engineered, but because they are simple. A lump of rock and ice, orbiting in darkness, can survive billions of years. If life, or intelligence, were to embed itself inside such a body, it might last as long. Perhaps the key is not to build against nature, but to build with it, using the cosmos as the protective casing. The philosophical implications are haunting. Imagine that civilizations are brief sparks, burning brightly for a few thousand years before fading. Their planets change, their stars evolve, their cultures vanish. But their machines, if designed well, become their fossils, their legacy. They drift through eternity, mute reminders that someone was here once, someone capable of thought and craft. The civilizations themselves may be forgotten, but their machines remain, outlasting not only their creators, but entire galactic eras. It's tempting to compare this to leaving a message in a bottle, a fragile note sealed in glass, cast into an endless ocean. On Earth, that bottle might last years before breaking apart. In space, the bottle could be a comet, and the message a probe designed to endure. Whether or not anyone finds it is another matter, but the act itself is an assertion. We were here. We left something behind. And that may be the most striking idea, that machines which outlast civilizations do not need to be elaborate. They only need to endure. A simple probe, wrapped in protective layers, could outlive entire galaxies of life, drifting silently through time. When we look at Atlas, we see a natural comet, but we also see the possibility that objects like it, icy, anonymous, ancient, might hide more than dust and gas. They might hide machines that have watched the universe change, waiting longer than we can fathom. The question is not whether such machines exist, but whether we would even recognize them if they passed before us. To our eyes, they would look like comets, asteroids, or fragments of rock, perfect disguises, silent survivors, testaments to civilizations whose names we will never know. And perhaps, in the glimmer of Atlas, we are reminded of that possibility, that the universe may be full of machines older than stars, drifting among us, carrying legacies across the darkness, built not to impress, but simply to last. Symbols in the chemistry. When scientists study a comet like 3I Atlas, they usually focus on the chemistry as a key to its origins. Ratios of water, carbon dioxide, carbon monoxide, and more exotic ices reveal the environment where it formed. In this sense, chemistry is a natural archive, a fingerprint left by cosmic history. But there is a more radical idea, one that stretches the line between science and speculation. What if these chemical fingerprints were not just natural records? What if they were messages? Think of it in terms of language. Humans long ago discovered that abstract symbols, marks on clay tablets, letters on parchment, could preserve meaning across time. A string of lines and curves can tell a story if you know how to read it. Chemistry, too, is made of symbols. The arrangement of atoms, the ratios of molecules, the dominance of one compound over another. These are patterns, and patterns can be deliberate as well as accidental. With Atlas, one of the strangest findings was its overwhelming carbon dioxide dominance. Compared to the water-rich comets of our solar system, Atlas seems inverted, almost as though it carries a message written in imbalance. If comets are natural time capsules, Atlas is like a book whose pages are filled with unusual, repeating glyphs. And here is the provocative question: what if someone, or something, knew we would read those glyphs? The idea may sound wild, but consider how humans have already attempted something similar. The Voyager probes, launched in the 1970s, Each carry a golden record with sounds and images from Earth. The records are analog, etched with patterns that can be decoded into pictures and sounds. But what if, instead of carrying a visible artifact, you embedded the message in the probe's chemistry itself? A civilization advanced enough to manipulate comets at their birth could leave behind ratios of elements that scream, "This is not natural." To the casual observer, it looks like a comet. To a curious, scientifically literate species, it looks like a signal. Imagine, for instance, a comet with hydrogen and oxygen in perfectly balanced ratios designed to suggest water but held in unnatural stability, or one with noble gases in proportions that do not occur in nature, creating a kind of molecular Morse code. Even more compelling, what if the carbon-to-oxygen ratio itself, like Atlas's bizarre skew, was not just an accident of formation but a deliberate symbol, chosen because it would confuse us, force us to notice, compel us to ask questions? This is not so different from how humans leave marks in the world. Archaeologists studying ancient ruins often wonder whether a pattern in stone placement is functional or symbolic. Is a line of stones a wall, or is it a message? Is an arrangement of bones a simple burial, or is it ritual? The same could apply to chemistry. Most of it is natural, but once in a while something may stand out, not because it is impossible, but because it is improbable. And improbability is often the first whisper of design. Of course, the scientific community remains cautious. Extraordinary claims require extraordinary evidence, and so far, every chemical fingerprint we've seen can be explained by natural processes. Atlas may be unusual, but it still fits within the realm of the possible. Yet the idea of chemistry as code forces us to look more carefully, to ask whether we are missing the forest for the trees. Are we so focused on what comets tell us about stars and planets that we overlook the possibility that they might also carry intentional meaning? It is worth noting that chemistry is universal. Unlike language, which differs from culture to culture, the behavior of atoms and molecules is the same everywhere in the cosmos. Hydrogen bonds the same way in another galaxy as it does on Earth. Carbon dioxide has the same spectral signature whether it is on Mars, Venus, or in an interstellar comet. If you were a civilization wanting to leave a message for anyone, anywhere, you could hardly choose a better medium than chemistry. It is the one language guaranteed to be understood, and in a sense, humans already read chemistry like symbols. Astronomers speak of abundance ratios as though they were sentences. A star rich in heavy elements tells us it is older. A comet with nitrogen deficiency tells us it formed in a warmer region. We already treat chemistry as narrative. The only step further is to ask whether some of those narratives were written deliberately. Perhaps Atlas is simply a natural comet, carrying nothing more than the frozen fingerprint of its ancient birthplace. But perhaps not. Its chemistry is strange enough to make us pause, to notice the imbalance, to ask why. And in asking, we are forced to entertain the possibility that the cosmos may not just be speaking through physics and chance, but through intention, through symbols hidden in ice and dust. If that were true, it would change the way we look at every comet. Instead of seeing them only as geological samples, we would begin to scan them like ancient tablets, searching for patterns too precise to be accidents. We would ask not just where they came from, but who might have left them. And in that search, the line between natural science and cosmic archaeology would blur. Even if Atlas proves entirely natural, the idea lingers like a haunting melody. Chemistry as code, molecules as symbols, comets as messengers, not just of star systems, but of thought. Perhaps that is their deeper mystery, that in their frozen cores they hold not only the memory of creation, but also the potential for communication, waiting for us to learn how to read. When nature deceives us. The human imagination is quick to leap toward meaning. When we see a strange shape in the clouds, a flicker of light in the dark, or an unfamiliar sound at night, our first instinct is not always to assume chance, it is to assume intention. This tendency has served us well throughout history. The rustle in the grass might be the wind, but if it is a predator, it pays to assume the worst. Yet when we carry this instinct into the cosmos, it sometimes leads us to misinterpret nature's oddities as signs of design. The history of astronomy is filled with such cases, moments when something looked so strange, so unnatural, that even seasoned scientists considered artificial origins. These stories remind us that the universe is clever in ways we don't always expect, and that 3i Atlas, for all its bizarre chemistry, may simply be another example of nature's creativity rather than a probe in disguise. One of the most famous examples is pulsars. In 1967, Jocelyn Bell Burnell detected a steady, rhythmic signal from space, a pulse so precise that her team jokingly labelled it LGM1, short for Little Green Men. The regularity of the signal seemed mechanical, like a beacon or transmission. For months, speculation simmered. Could this be evidence of extraterrestrial intelligence? But the truth, once uncovered, was just as fascinating, if not more so. Pulsars are rapidly rotating neutron stars, collapsed stellar cores that emit beams of radiation sweeping across space like cosmic lighthouses. What looked like a transmission was, in fact, a natural clockwork of unimaginable density and power. Another case came with quasars in the 1960s. These extraordinarily bright points of light looked like stars, but with strange redshifts, suggesting they were impossibly far away, and therefore impossibly luminous. Some wondered if they might be technological constructs, artificial power sources. In reality, quasars are powered by supermassive black holes, consuming matter at galactic centers, their light amplified by forces beyond human engineering. Again, what looked artificial was revealed to be natural, but no less astonishing. Even within our own solar system, deceptions abound. For decades, observers thought they saw canals on Mars, straight lines crisscrossing the planet's surface. The idea of a Martian civilization captured the public imagination, with maps and theories of irrigation networks drawn in detail. But as telescopes improved, the canals vanished. They were optical illusions, the brain's tendency to connect faint features into straight lines. Nature had tricked us, not through intent, but through our own perception. Closer to comets, there have been countless examples of strange behavior misread as deliberate. Unexplained outbursts, fragments breaking off suddenly, or bizarre trajectories often inspire whispers of control or hidden purpose. Oumuamua's odd acceleration, for instance, sparked real debate over whether it could be artificial. But each time, nature has offered explanations: unusual ices, sublimation forces, or structures we had not anticipated. Atlas, with its carbon dioxide dominance, may feel alien, but history urges us to look carefully before we assume intent. These lessons do not diminish the excitement of discovery, they deepen it. When pulsars turned out to be neutron stars, the result was not disappointment but awe. When quasars were revealed as black holes, our understanding of the universe expanded dramatically. What we learn in these moments is that nature is capable of creating phenomena that rival and often surpass the imagination of science fiction. So, what does this mean for Atlas? It means we must tread carefully. Its unusual chemistry, its hyperbolic path, its fleeting visibility, all of these features tempt us to speculate about messages, probes, or design. But before we jump to conclusions, we should remember that the universe has tricked us before. If Atlas defies our expectations, it may not be because it was built. It may be because our expectations were too narrow. Still, there is a beauty in these mistaken leaps. They remind us of our hunger for connection, our desire to find meaning in the vastness, and occasionally they push science forward. Pulsars were not signals, But the search for signals led to their discovery. Oumuamua was not a spacecraft, but the debate forced us to sharpen our methods, to think critically about how we would tell the difference. Even when nature deceives us, it teaches us. Perhaps then, the lesson of Atlas is not whether it is artificial or natural, but how we respond to the unknown. Do we close the door on strange ideas too quickly, or do we remain open, curious, willing to test the improbable? The balance is delicate. Too much skepticism, and we risk missing the extraordinary. Too much imagination, and we risk fooling ourselves. The dark forest hypothesis. Imagine walking alone at night through a vast, silent forest. The trees stretch endlessly in every direction, and the darkness is so deep that you cannot tell who else might be out there. Perhaps there are other travelers, some friendly, some hostile, some too strange to even understand. In such a forest, how would you act? Would you shout, announce yourself, wave a torch to let others know you're there? Or would you stay quiet, hiding in the shadows, hoping no one notices? This is the essence of the dark forest hypothesis, a chilling idea from modern astrobiology and philosophy of science. It suggests that the universe is like that forest, teeming with civilizations, but all of them silent, cautious, hiding from potential predators. In such a universe, to broadcast your presence would be reckless, even suicidal. The safest strategy is to listen, to watch, to remain unseen. And here is where 3I Atlas enters the picture. What if this interstellar comet is not merely a fragment of ice and dust, but something more? What if it is a scout, a silent messenger drifting through space, recording what it sees, careful never to betray its origins? In a universe where silence is survival, comets might be the perfect camouflage. The hypothesis rests on a few sobering assumptions. First, civilizations that reach advanced technological levels will likely develop the means to destroy each other and others. Second, resources in the universe are finite, and competition, however rare, may lead to aggression. Third, and most crucial, you can never know the intentions of another civilization. A friendly neighbor may remain friendly for centuries, only to change later. The only way to guarantee safety is to assume the worst, that every other intelligence could be a threat. If you accept those assumptions, the dark forest becomes inevitable. Civilizations do not announce themselves. They send out scouts cloaked in silence. They avoid signals that might betray their position. And if they detect another civilization that is loud, they may act first, eliminating the potential danger before it becomes real. In this vision of the cosmos, survival depends on invisibility. So what would a scout look like in such a scenario? It would need to blend seamlessly with its environment. It could not appear as a shining machine or an obvious artifact. It would have to look like something ordinary, something expected. And what is more ordinary in the cold reaches of space than a comet? Comets are everywhere, natural debris flung from planetary systems, frozen bodies wandering the void. A probe disguised as one would slip past suspicion, gathering information while remaining invisible. Atlas, with its strange chemistry and interstellar origins, naturally invites such speculation. Could its bizarre carbon dioxide dominance be part of the disguise? A way to look different enough to be ignored as a curiosity, but not so different as to reveal intention. Could its hyperbolic trajectory be not just an accident of formation, but a path chosen for reconnaissance, allowing it to pass close to stars without ever circling back? Of course, there is no evidence that Atlas is anything but natural, but the dark forest hypothesis pushes us to consider not what is likely, but what would make sense in a universe where silence is survival. From that perspective, comets are not just icy relics. They are ideal scouts, durable, inconspicuous, able to survive for billions of years, able to wander without arousing alarm. And if this hypothesis holds, then the quietness of the universe, the so-called Great Silence, is no mystery at all. We do not hear signals because civilizations do not send them. We see no grand beacons because to build one would be to paint a target on your back. Instead, we are surrounded by silence, a silence not of emptiness, but of caution. The forest is alive, but all its creatures hide. For us on Earth, the idea is unsettling. We have sent signals into the void, radio broadcasts, radar pings, even the Voyager records, golden discs carrying our address in the cosmos. If the dark forest hypothesis is true, those acts may have been dangerously naive. Like lighting a torch in the forest, they announce, "Here we are." And though no one may have noticed yet, the forest is wide and echoes travel slowly. Perhaps Atlas is only a comet. Perhaps it is nothing more than an icy traveller born in a distant system, a wanderer shaped by forces we only partly understand. But as it passes us, silent and strange, it invites us to reflect on the nature of survival in the universe. If the dark forest is real, then objects like Atlas may not just be debris. They may be watchers, quiet, enduring scouts, carrying the silence of their makers across the stars. And in that thought lies both wonder and fear. Because if the universe is a dark forest, then every flicker of light we see in the sky, every comet, every wanderer, could be more than it seems. And perhaps the most important question is not what is Atlas, but who might be watching through it. Microseeds, the invisible invasion. Since the dawn of human curiosity, comets have been seen as both givers and takers. In the ancient world, they were omens of change, sometimes feared as harbingers of disaster, sometimes revered as cosmic messengers. Today, science offers a new perspective, one that is equally awe-inspiring and unsettling. Comets may not just carry ice and dust, but also the very seeds of life. And if they can carry seeds, they might also carry something far more dangerous. The idea is called panspermia. It suggests that life on Earth may not have started here at all. Instead, it may have arrived long ago, carried by comets or meteorites that struck the young planet. The frozen ices inside these objects could shield fragile organic molecules from cosmic radiation, preserving them for billions of years as they drift through the void. When they finally collided with a hospitable world, those molecules could spark the chemistry of life. For many scientists, panspermia is not just possible, but plausible. We already know that comets are rich in the ingredients of biology. Amino acids, sugars, and other complex organics have been detected in their tails and cores. In this view, comets are like delivery ships scattering microseeds across the galaxy, planting possibilities wherever they land. But what if we expand that idea? What if the seeds are not merely natural molecules but something engineered? What if an advanced civilization seeking to spread itself across the stars used comets as carriers not of ice and rock but of nanotechnology? Self-replicating machines so small we might mistake them for dust. In this darker vision, the invisible invasion begins not with a roar, but with a whisper. A comet like 3I Atlas passes silently through the solar system, shedding fragments of ice and dust as it warms. Within that dust, invisible to the eye and nearly impossible to detect, lie microscopic machines designed to endure and to spread. They drift down through atmospheres, settle into oceans, and wait. Unlike biology, they do not need to adapt. They are already built to survive. This idea is speculative, yes, but it emerges from principles we already understand. On Earth, nanotechnology is still in its infancy, but scientists are developing machines the size of molecules, capable of manipulating matter atom by atom. We imagine medical nanobots that could heal cells from within, or environmental nanobots that could clean oceans. But if we can imagine such things, then perhaps other civilizations, older, more advanced, have already built them. And what better way to distribute them across the stars than inside comets, the natural travelers of the galaxy? The unsettling part is how invisible such an invasion would be. We are used to thinking of threats as large, obvious, catastrophic. An asteroid impact leaves a crater, a supernova floods the sky with light, but a dust grain carrying engineered microseeds would pass unnoticed, indistinguishable from the countless other grains that rain down on Earth every day. It would not need to conquer quickly, it would simply persist, waiting for its moment. Of course, panspermia in its natural form is not sinister. It is beautiful. It suggests that life is not confined to one world, that the galaxy may be full of distant cousins sharing the same ancient spark. Perhaps Atlas carries nothing more than this gift, simple chemistry, ready to bloom if it ever finds soil fertile enough to grow. But once we add the possibility of intent, of design, the picture changes. The same mechanism that could spread life could also spread control. There are echoes of this idea in human culture. Myths of seeds that carry both nourishment and poison, stories of gifts that conceal hidden dangers. Even in biology, the line between symbiosis and parasitism is thin. A seed can feed a forest, or it can strangle it. The question is not whether comets can carry seeds, but whether those seeds are benign or something else entirely. For now, science has found no evidence of alien nanotechnology. Every comet studied so far, including Atlas, has behaved like a natural body. Its chemistry, however strange, fits within the boundaries of physics and geology. And yet, the possibility lingers because it makes sense in principle. If civilizations wanted to reach across the galaxy without building vast ships, comets would be their vehicles. They are abundant, durable, and already programmed by nature to spread material from one system to another. To think of them as carriers of life is hopeful. To think of them as carriers of machines is sobering. But both ideas remind us that comets are not just frozen relics. They are potential agents of change, capable of shaping worlds in ways we barely comprehend. And so, as Atlas fades into the cosmic night, we are left with questions that cut both ways. Did comets bring us here, seeding Earth with the first whispers of life? Or could they one day carry something less benevolent, an invisible invasion written not in DNA but in code, hidden in the dust we welcome as ordinary stardust, the Great Filter? In the silence of the night sky, as 3I Atlas drifts past our solar system on its lonely, hyperbolic path, a question lingers like a shadow. Why is it so alone? If the galaxy is vast, with countless stars and planets, why do we not see evidence of thriving civilizations all around us? Why is Atlas just a comet and not an emissary? This question lies at the heart of one of the most sobering ideas in astrobiology, the Great Filter. It is the unsettling suggestion that somewhere along the journey from simple chemistry to galaxy-spanning civilization, there is a barrier so high, so difficult to cross, that almost no species makes it past. The silence we observe is not a mystery of chance, it is the echo of billions of failures. The filter can exist at many stages. Perhaps it sits behind us, and life itself is the rare miracle. Maybe Earth is unusual, not because it harbors intelligent beings, but because it harbors life at all. If that is true, then comets like Atlas are lonely for a reason. The galaxy is mostly sterile, filled with ice and rock, but devoid of biology. In that scenario, the Great Filter is already behind us, and we are extraordinarily lucky. But what if the filter lies ahead? What if the steps from intelligence to survival are far harder than we imagine? Civilizations may rise, build tools, send probes, even flirt with space travel, but then collapse before they spread. War, Resource exhaustion, environmental collapse, or the misuse of their own technology could all extinguish them before they make themselves known. In that case, Atlas's silence becomes haunting. It passes through our solar system not just as an icy wanderer, but as a reminder that others may have come before us and are gone. Comets are fitting metaphors for this. They are survivors of chaos, fragile bodies that endure against the odds. Yet most comets break apart, colliding with planets or disintegrating in sunlight. Only a few remain intact long enough to cross interstellar space. Civilizations may be the same. Many may flicker briefly, bright as a comet's tail, before burning out. Only the rarest might endure long enough to spread their influence widely. Perhaps the galaxy is full of civilizations that began but never lasted, their traces erased like a comet's fading streak in the sky. The great filter forces us to look at ourselves with uncomfortable honesty. We are a young species, barely a few 100,000 years old, and only in the last century have we begun to explore space. Already we face challenges that could undo us: climate change, nuclear weapons, resource depletion, and technologies we do not fully understand. If the filter lies ahead, these threats may not just be human problems, they may be universal traps, the same pitfalls that erased countless others before us. And yet, the idea of the filter is not entirely bleak. If we recognize it, we can fight it. Perhaps civilizations that survive do so by mastering cooperation, restraint, and foresight. Perhaps survival requires not just intelligence, but wisdom, the ability to see past immediate desires and protect the long future. Atlas, in this sense, becomes not just a visitor, but a mirror. Its endurance across billions of years shows us what survival looks like: patience, resilience, simplicity. There is another angle too. What if the filter is not a single barrier, but many small hurdles stacked together? Life may be rare, intelligence rarer still, technology rarer again. Each step reduces the number who pass through until only a few reach the stars. If this is true, then perhaps the filter is not ahead or behind, but scattered along the path, making our presence here an extraordinary improbability. In this light, Atlas is not just a comet. It is a symbol of how rare survival truly is. Out of countless fragments flung into space, only a few ever wander far enough to be seen. Out of countless civilizations, perhaps only one or two ever last long enough to make contact. What does this mean for us as we watch Atlas fade back into the dark? It means that we must take our place in the cosmos seriously. If the filter is behind us, we may be the lucky few. If it lies ahead, we must prepare. And if it is scattered across time, then each step we take toward endurance is more precious than we know. The Great Filter is not just a theory, it is a story about fragility and resilience. Comets like Atlas embody that tension. They are fragile, prone to breaking, yet capable of surviving longer than stars. Civilizations may be the same. The question is whether we will be like the countless comets that vanish in sunlight, or like the rare ones that endure, traveling further than anyone imagined. Messages from the dead. Picture 3i Atlas not just as a comet, but as a relic, an ancient bottle cast into a cosmic ocean. Its icy shell and strange chemistry may appear natural, but what if beneath that surface lies something older than human history, older even than Earth itself? What if Atlas is not a random traveler at all, but a message launched by a civilization that vanished long before our sun was born? This possibility is unsettling because it forces us to expand our sense of time. We humans live within decades, our civilizations endure for centuries, our monuments stretch across millennia. But the universe measures time in billions of years. Entire galaxies evolve and transform while worlds rise and fall. A civilization could have emerged around some distant star 3, 4, even 5 billion years ago, flourishing, discovering, reaching for the sky, and then disappeared, leaving behind only artifacts. If such a people existed, their remains would not be found in ruins or monuments, but in the things most likely to survive: machines, probes, and wandering messengers like Atlas. Think of Earth's own trajectory. If humanity were to vanish tomorrow, our cities would crumble within centuries. Within 1,000,000 years, almost every trace of our existence on the surface would be gone, swept away by geology and biology. Yet the spacecraft we've sent into deep space, the Voyagers, the pioneers, would continue to drift, mute witnesses to a civilization long extinct. For billions of years, they would wander the interstellar dark. To anyone who found them, they would not speak of a living humanity, but of one long gone. They would be, in essence, messages from the dead. Atlas could be such a message. Its hyperbolic path suggests it has travelled for eons, perhaps from one side of the galaxy to another. It may have been flung free of its home system by a giant planet, just as our own Jupiter hurls comets into interstellar space. But what if that ejection was not accidental? What if someone sent it deliberately, not as a weapon, not as a scout, but as a memorial? A civilization facing extinction might choose to seed the stars with reminders of their existence, hoping that someone, someday, might notice. The haunting thought is that such a message might not even need to be readable. A strange chemical fingerprint, like Atlas's unusual carbon dioxide dominance, could itself be the signature. Not a word, not a sentence, but a whisper. We were here. To us, it looks like an oddity of formation. To them, it might have been a deliberate mark, one designed to outlast everything else they created. It is worth remembering that the universe itself has no shortage of messages from the dead. The light we see from distant stars is already ancient, carrying news of suns that may no longer exist. The heavy elements in our bodies, iron, calcium, oxygen, were forged in supernovae, the fiery deaths of massive stars billions of years ago. We are, in a very literal sense, already built from messages left by cosmic ancestors. Extending this idea to civilizations is not such a leap, and yet there is a bittersweet edge to the thought. If Atlas were such a message, it would mean that its creators are gone. They may have been brilliant, capable of harnessing comets and mastering interstellar travel, but time erased them. Their worlds may be dust, their names forgotten, their cultures lost. All that remains is an icy fragment, drifting silently past our skies. We would not know what they believed, what they dreamed, or how they lived. We would only know that they were. There is something profoundly human in this line of thinking. We too leave messages for the unknown future. The Voyager golden records carry greetings in dozens of languages, music from across cultures, diagrams of our place in the galaxy. These are not just scientific data, they are memorials, artifacts designed to outlast us. If another species one day finds them, it will not meet living humans. It will meet our echoes, our attempt to say, once we existed. In that sense, Atlas's passing through our solar system may feel like a mirror. It makes us consider the fragility of civilizations and the brevity of cultural memory. Perhaps what matters most is not how long a species survives, but what it leaves behind. For one civilization, the gift might have been Atlas. For us, it might be the Voyagers. Both are tiny, fragile objects against the enormity of space. Yet both carry meaning greater than their size. The irony is that we may never know for certain whether Atlas is natural or intentional. Its message, if one exists, may be beyond our ability to decode. Perhaps its senders understood this. Perhaps they knew that after billions of years, their words would fade, their technology would erode, and only ambiguity would remain. But even that ambiguity serves as a message. Life once stirred, once wondered, once reached for eternity. And so, as Atlas recedes into the dark, we are left with a choice. We can see it as a comet, nothing more, a fragment of ice flung across the galaxy. Or we can see it as something deeper, a reminder that civilizations rise and fall, that messages outlast their senders, and that we too are writing our own epitaphs in the cosmos, whether we realize it or not. Humanity's greatest diplomatic test. Imagine for a moment that tomorrow astronomers announce the unthinkable. 3I Atlas is not just a comet. Beneath its icy skin lies structure, something regular, geometric, unmistakably artificial. In an instant, everything would change. The headlines would ripple across the planet. Governments would scramble, and billions of people would look up at the sky with awe, fear, or hope. The discovery would not just be scientific, it would be political, cultural, and existential. The question that would immediately follow is as simple as it is overwhelming. Who speaks for Earth? History gives us little precedent. On our own planet, when cultures have encountered each other across oceans and continents, first contact has almost always been messy. Sometimes it was violent conquest, sometimes cautious trade, sometimes mutual misunderstanding. But there has never been a moment where an entire species had to agree on a voice, a single representative to address something greater than itself. We are used to nations speaking for themselves, not for everyone. If Atlas were artificial, the nations of Earth would each feel pressure to claim a seat at the table. The United States, with NASA and its global influence, might argue that it should lead. China, with its rapidly advancing space program, would not stay silent. Russia, Europe, India, and others would demand a role. The United Nations might try to mediate, but consensus among nearly 200 countries is slow and fragile. In the meantime, the object would be drifting past, silent, as humanity argued over who gets the microphone. Scientists would offer another perspective. They would insist that communication should not be filtered through politics, but handled carefully, collectively, with transparency. Organizations like the SETI Institute have quietly drafted protocols for such scenarios, guidelines that emphasize patience and shared responsibility. But those guidelines are voluntary, and in a real crisis, political interests tend to overshadow patient science. A single nation might act on its own, broadcasting signals toward Atlas before others could agree on whether that was wise. The irony is that the object itself, if it truly were artificial, might not care who speaks. It might not even be listening. It might be dormant or indifferent, or designed to observe rather than converse. Yet the struggle on Earth would be real, and it would reveal much about us. Would we see ourselves as a fractured world of competing nations, or as one civilization, however imperfect, facing the cosmos together? Some argue that we are not ready for such a test. The divisions between us run deep, ideological, religious, cultural, economic. Even within nations, consensus is rare. How then could we present a unified voice? Perhaps the answer is that we cannot. Perhaps no single message could represent 8 billion perspectives. Maybe silence, at least at first, would be wiser than trying to choose one voice too soon. And yet, there is another way to look at it. Crises have a way of forcing cooperation. During the Cold War, the United States and the Soviet Union, locked in nuclear rivalry, still managed to work together on space exploration. Apollo-Soyuz in 1975, the International Space Station decades later, both showed that even bitter rivals can collaborate when the stakes are high enough. If Atlas revealed itself as artificial, perhaps the very weight of the moment would compel unity, however temporary. For once, our divisions might seem trivial against the immensity of contact with something not of Earth. Of course, the danger would lie not only in who speaks, but in what they say. Do we greet Atlas as equals? Do we beg for knowledge? Do we express fear or curiosity or reverence? Words carry weight, and the first words of humanity to another intelligence could echo across millennia. A cautious greeting might be seen as wisdom, a boastful declaration might be seen as arrogance, and silence itself could be interpreted in ways we cannot control. There is also the question of whether we should speak at all. Some thinkers warn against it, invoking the dark forest hypothesis. If the universe is dangerous, announcing ourselves could invite disaster. Perhaps the best diplomatic move is to remain quiet, to let Atlas pass without drawing attention. But that too is a decision, a choice about how humanity presents itself, not through words but through restraint. In the end, the greatest diplomatic test may not be with Atlas itself, but with ourselves. Can we cooperate across borders and beliefs? Can we set aside ego and fear long enough to act as a species rather than as tribes? Can we recognize that the first contact, if it comes, will not be about who leads, but about what it means to be human in a wider cosmos? If Atlas is artificial, the comet would not just be a visitor. It would be a mirror forcing us to confront how we see ourselves, how we act under pressure, and how ready or unready we are for the greatest conversation in history. Containment versus curiosity. When 3I Atlas was first confirmed as interstellar, the initial excitement was scientific. Here was a traveler from another star system, a chance to study material untouched by our sun, older than our own planets, perhaps carrying secrets of alien chemistry. But beneath the thrill lurks a quieter, more difficult question. How should humanity respond to such a visitor? Should we rush to learn everything we can, embracing Atlas as a rare gift of discovery? Or should we treat it with extreme caution, fearful of contamination from something utterly foreign? This tension between containment and curiosity echoes throughout human history. When explorers crossed oceans, they brought with them not just goods and ideas, but also diseases that devastated populations unprepared for them. The Columbian exchange between the old and new worlds was as much a biological catastrophe as it was a cultural encounter. Nature does not care about intent. Even the smallest microbe can reshape entire civilizations. The same principle applies on a cosmic scale. If Atlas carries organic material, or worse, active biological agents, they would be unlike anything on Earth. Our immune systems, evolved for our biosphere, would have no defenses. Even a molecule stable in interstellar conditions could interact unpredictably with Earth's ecosystems. The smallest fragment of alien chemistry might prove disruptive in ways we cannot foresee. For this reason, planetary protection policies exist. NASA and other space agencies handle every mission with sterilization protocols, both to prevent Earth microbes from contaminating other worlds and to avoid bringing back anything hazardous. The Moon, Mars, even distant asteroids are treated with caution. An interstellar comet like Atlas would magnify those concerns 1,000-fold. Its material does not belong to our solar system at all. It is the very definition of the unknown. And yet, the lure of curiosity is irresistible. What if Atlas holds the building blocks of life, or evidence that life itself is common across the galaxy? What if its unusual carbon dioxide dominance is more than a quirk, but a clue to exotic chemistry we have never imagined? To let such a visitor pass without studying it closely would feel like negligence. For scientists, the risk of contamination is not only a danger, it is an opportunity. Every comet is a time capsule. An interstellar one is a library written in a language we may never encounter again. So the debate becomes philosophical as much as practical. Do we lean toward caution, building containment vessels and treating Atlas like a potential threat? Or do we lean toward openness, welcoming it as a teacher? Both paths carry costs, too much caution, and we may lose a chance to answer some of the deepest questions of existence. too much curiosity, and we may invite risks we cannot control. Perhaps the answer lies in balance. Imagine a sample return mission designed like a quarantine, a robotic spacecraft intercepting Atlas, sealing fragments in layers of sterile chambers, returning them to labs built underground in isolation. Scientists could study the material without ever exposing Earth directly. Such missions are already being considered for Mars, where the fear of back contamination is real. Applied to Atlas, the protocols would be even stricter. But containment has limits. No system is perfect, and absolute safety is an illusion. The act of studying is itself a form of risk. Even opening the comet's secrets remotely through spectroscopy, telescopes, or instruments in orbit exposes us to ideas, to knowledge. And knowledge can be as transformative and as dangerous as microbes. What we learn from Atlas might change how we see life, the universe, even ourselves. In that sense, curiosity is unavoidable. We cannot not look. This struggle between fear and wonder is deeply human. When we discovered fire, we feared its destruction but embraced its warmth. When we unlocked nuclear energy, we feared its devastation but used it to power cities. Every step forward has carried shadows. Atlas is no different. It is both threat and gift, danger and opportunity. To treat it as only one or the other is to miss the truth. And so, perhaps the real challenge is not containment versus curiosity, but containment with curiosity. To approach Atlas with humility, acknowledging that we do not know enough to be reckless, but also with openness, recognizing that the universe rarely offers gifts so rare, to fear without paralysis, to wonder without carelessness. The absence of signals. When Oumuamua passed through our solar system in 2017, one of the first things astronomers did was listen. Radio telescopes scanned it for signs of transmissions, hoping for even the faintest whisper of intention. Nothing came. When 2I/Borisov followed in 2019, the same process unfolded. Again, silence. Now, with 3I Atlas, the pattern continues. Despite its unusual chemistry, despite its intrigue, the comet remains mute. At first glance, this silence might seem unsurprising. After all, comets are not supposed to talk. They are frozen fragments of rock and ice, natural wanderers without voices. But in cosmic terms, silence is not always so simple. Silence itself can carry meaning, and sometimes what is not said can be more revealing than what is spoken. Consider human history. In diplomacy, silence can signal disapproval or caution or refusal to engage. In relationships, silence can wound more deeply than words. Even in art, silence, like the pause in a symphony, can create tension or anticipation. Communication is not only about signals, but about their absence. If the cosmos is a conversation, then the absence of signals is a language of its own. One interpretation is the simplest. There truly is no one to speak. Atlas is a natural object, a relic of a distant system, and silence is merely the sound of emptiness. Yet, for those who entertain the possibility of intelligence, silence can be deliberate. If the dark forest hypothesis holds, civilizations may hide to avoid predators, avoiding any emissions that could reveal their position. A comet like Atlas would then be the perfect disguise, silent, anonymous, drifting through space without drawing attention. There is also the possibility that signals are there, but we do not know how to hear them. Our technology is tuned to certain frequencies, certain forms of communication. We expect radio waves, laser pulses, or obvious beacons. But an alien civilization might use physics we barely grasp, gravitational waves, neutrino streams, quantum entanglement. Their silence, from our perspective, could simply be a mismatch of language. Like listening for drums when the message is written in light, we might mistake quiet for absence. Another angle is that silence could be a form of test. Imagine a civilization seeding the galaxy with probes disguised as comets. If they remained quiet, their watchers could study how emerging species behave when faced with mystery. Do they panic? Do they fight? Do they cooperate? Do they attempt to communicate? In this sense, the silence is not indifference, but a deliberate mirror reflecting us back to ourselves. There is a haunting beauty in the idea that silence itself might be a message. Perhaps it says, "We are not ready," or "You must come to us," or even, "The universe is more dangerous than you think." Silence can carry warning as much as welcome. And in a cosmos where distances are vast and patience is measured in millennia, silence may be the safest, most universal form of communication. Of course, from the scientific perspective, silence is also data. Each time we scan an interstellar object and hear nothing, we refine our understanding of how common or rare signals might be. Silence accumulates into a pattern, a growing map of absence that shapes our expectations. The lack of signals from Atlas does not prove loneliness, but it adds weight to the possibility that we may indeed be alone, or that others are choosing not to speak. For humanity, the silence of Atlas is both comfort and challenge. Comfort because it suggests we are not under immediate threat from some active presence within the comet. Challenge because it leaves us with nothing but questions. If we are not hearing signals, should we send our own? If others remain quiet, does wisdom lie in joining them or in breaking the silence first? Patterns in the dust. When most people think of a comet, they imagine a glowing streak across the night sky, its luminous tail stretching like a banner behind it. That tail is the product of outgassing, frozen ices warmed by a star turning to vapor, carrying dust into space. To the naked eye, it seems chaotic, a shimmering plume scattered by solar winds. But what if it isn't chaos at all? What if within those drifting clouds lies structure, patterns too subtle for us to notice, too alien for us to decode? It's an idea that feels almost whimsical, like seeing shapes in clouds. And yet, history warns us not to dismiss such possibilities too quickly. Nature often hides complexity within apparent randomness. The spiral of a seashell, the branching of a tree, the rhythm of a heartbeat, all are patterns concealed within what might first appear messy. If comets are potential messengers, then perhaps their dust trails are not just exhaust, but language. Imagine a civilization seeking to communicate without broadcasting radio waves, which could give away its position to unknown predators. Instead, it could encode information in physical phenomena, using nature itself as the medium. A comet passing through a star system offers a perfect vehicle. Its dust tail can be seen and measured with telescopes, and subtle variations in composition, density, or emission could carry meaning. To us, it looks like gas streaming away. To those who know the code, it could be a message written across millions of kilometers. There are precedents for such thinking in our own science. Astronomers study the light from stars through spectroscopy, breaking it into rainbow bands of color to reveal hidden patterns. In those lines, we find fingerprints of hydrogen, helium, carbon, every element telling a story of where it was forged. If starlight carries a code of chemistry, why couldn't cometary dust? Consider 3I Atlas specifically. Observations suggest its outgassing is dominated by carbon dioxide, far more than expected compared to water or carbon monoxide. That imbalance looks strange to us, but strangeness itself could be part of the design. Suppose a sequence of outbursts, first strong, then weak, then strong again, could mimic a binary signal. Suppose ratios of molecules, when mapped carefully, formed repeating sequences. To us, this is data. To another civilization, it might be as clear as letters on a page. Skeptics would argue that comets are chaotic by nature, their activity driven by sunlight and internal fractures. Randomness, not intention, shapes their plumes, but randomness itself can be harnessed. On Earth, we use variations in noise, in electrical pulses, even in the jitter of atoms to generate codes. If we can find meaning in fluctuations, then others could too. What seems to us like turbulence might be design hidden in plain sight. There's a parallel here with fireflies in a summer field. To someone unfamiliar, their flashes seem random, scattered sparks in the night. But to other fireflies, each blink is a signal, timed, patterned, filled with meaning. Only by learning the rhythm can we recognize the conversation. Atlas, streaming dust into the void, could be like those fireflies, signaling in a pattern we have not yet learned to read. The haunting part of this possibility is that we may already be surrounded by messages we fail to notice. If encoding is subtle, slight differences in brightness, variations in particle size, spectral shifts invisible to the eye, we might dismiss it as noise. We assume communication must be directed at us, in our languages, in our mathematics, but perhaps the cosmos has been whispering in patterns we don't yet understand. For now, scientists track Atlas with instruments that measure brightness, spectra, and shape. They look for physical clues, not hidden codes. And maybe that is all Atlas is, a natural wanderer shaped by sunlight and physics. But the thought lingers, if one day we find that comets carry messages in their dust, Atlas will be remembered not as silence, but as one of the first voices we failed to hear. Patterns can hide meaning, and meaning can change everything. In the swirl of cometary dust, in trails that seem chaotic but might not be, there could be libraries written in vapor and grain. And perhaps one day, when our instruments grow sharper and our imaginations wider, we will finally learn to read the language of the comets drifting past our world. Shadows of conspiracy. When news first broke of Oumuamua in 2017, it didn't take long for whispers of conspiracy to spread. Some wondered whether scientists knew more than they were saying. Others believed governments were deliberately withholding evidence of alien technology. In the years since, those whispers have only grown louder. Every interstellar visitor, from Borisov to Atlas, seems to invite not just scientific scrutiny, but also suspicion. Why? Because secrecy and silence create shadows, and in those shadows, people's imaginations rush to fill the gaps. When an object like 3I Atlas passes through our solar system, the story is naturally complex. Orbital mechanics, spectroscopy, chemistry, these are difficult subjects, hidden behind jargon and data charts. For most people, the details remain mysterious, and when something is mysterious, it becomes fertile ground for alternative explanations. Governments and space agencies know this, which is why they often emphasize cautionary language. NASA and the European Space Agency are careful to say there is no danger, no evidence of threat, nothing unusual. Their intent is reassurance, but reassurance, repeated too often, can backfire. The very act of stressing safety can feel like an attempt to hide the truth. It's like a neighbor insisting, again and again, that everything is fine. You start to wonder what they aren't telling you. Conspiracies grow strongest when three conditions overlap: fear, uncertainty, and partial secrecy. Atlas checks all three boxes. Fear comes from its interstellar nature, alien by definition. Uncertainty comes from its strange chemistry and trajectory. Partial secrecy comes from the fact that only a handful of observatories have the tools to study it, and much of that data trickles out slowly, filtered through academic papers few people can read. Into that vacuum of knowledge, conspiracy thrives. History offers countless examples. When Halley's Comet appeared in 1910, tabloids reported that its tail contained deadly cyanogen gas that might poison Earth. Panic ensued. Gas masks sold out. Some even sealed their windows, convinced the comet would suffocate them. No scientists had suggested such a danger, but the absence of clear communication left space for fear to bloom. The same dynamic exists today, magnified by the internet. Social media spreads rumors at the speed of light. Atlas is a disguised probe. Atlas is hiding signals. Atlas's trajectory was altered. A photograph of its dust trail becomes evidence of technology. A delay in publishing results becomes proof of a cover-up. In online forums, speculation hardens into belief. The truth struggles to compete, not because it is weak, but because it is less dramatic. And yet, conspiracy thinking isn't only about fear, it is also about control. To believe in hidden truths is to feel you have special access, a way of seeing what others miss. In a universe so vast and indifferent, that feeling of control is comforting. If Atlas is just a comet, then it is random, meaningless, another cold visitor passing by. But if Atlas is the subject of a cover-up, then it suddenly matters, and so do the people uncovering the truth. For scientists, the challenge is delicate. To dismiss conspiracies too harshly risks deepening distrust. To ignore them risks letting misinformation spread unchecked. The best antidote is openness, sharing data widely, explaining methods clearly, and acknowledging uncertainty honestly. But openness has limits. Even scientists do not know everything about Atlas, and uncertainty, no matter how honestly presented, often feeds suspicion rather than easing it. The irony is that secrecy and conspiracy are reflections of each other. If scientists and governments say little, conspiracies rush in to fill the silence. If they say too much, conspiracies twist their words into new fuel. In this dance, the comet itself remains silent, while humans project onto it their hopes, fears, and suspicions. Atlas, drifting through the night sky, doesn't care about our narratives, but our response to it, our tendency to weave shadows of conspiracy around an icy fragment of rock, reveals more about us than about the comet. It shows how deeply we crave meaning, how quickly we mistrust authority, and how fragile the line is between science and speculation. Cosmic archaeology. To think of 3I Atlas as a comet is the safe scientific thing to do. It is, after all, a lump of frozen gas and dust, glowing faintly as it reacts to the sun's warmth. But there's another way to frame it, one that shifts our perspective entirely. Instead of seeing Atlas as just an object, we can see it as an artifact, a relic from a galactic past that predates even the birth of our sun. In that sense, studying Atlas becomes an act of cosmic archaeology. On Earth, archaeology is the practice of uncovering human history through fragments, pottery shards, bones, ruins half buried in sand. None of these objects tell their story outright. Instead, they whisper clues. A carved tool reveals not just its use, but the culture that shaped it. A collapsed wall reveals not only decay, but also the ambitions of its builders. Archaeology is a discipline of inference, of piecing together lives long gone from what they left behind. Now, extend that mindset to the stars. Our solar system is young by cosmic standards, just 4.6 billion years old. But the Milky Way is much older. Long before the Sun was born, other stars formed, lived, and died. Their systems too must have had comets, asteroids, and planets. Some of those systems were chaotic, ejecting material into interstellar space. Over billions of years, those fragments drifted outward, crossing gulfs of darkness. Atlas may be one of them, a shard of a system older than our own, a survivor from a galactic chapter we were never meant to witness. If that is true, then Atlas is not simply a comet. It is a fossil of another world. Its chemistry is not random, but a fingerprint of conditions that no longer exist. When scientists point telescopes at its dust and vapor, they are reading a record of ancient physics and chemistry, preserved like writing on stone. Just as archaeologists can reconstruct a lost civilization from broken artifacts, astronomers can reconstruct a lost star system from objects like Atlas. Think of it this way. If someone 1 billion years from now were to study fragments of our own comets, they would find traces of Jupiter's influence, the Sun's heat, and Earth's chemistry. They would see, in miniature, the story of our system. Atlas offers the same, but from a star that may have burned out long ago. Its parent world might no longer exist. Its star might have gone supernova or collapsed into a white dwarf. Atlas might be the last survivor of a place erased from the galaxy. This makes comets more than just icy wanderers. They are time capsules, carrying messages not from civilizations, but from nature itself. Atlas may tell us about what stars were made of billions of years ago, when the Milky Way was still turbulent, still mixing its heavy elements. Its unusual carbon dioxide dominance might reflect a different recipe for planet formation, one no longer common today. In this sense, studying Atlas is like uncovering the ruins of a forgotten city, except the city is a solar system, and the ruins are scattered across light years. And yet, there is something poetic in this comparison. Just as archaeologists brush sand from bones, astronomers sweep away the dust of distance with telescopes. Just as archaeologists reconstruct vanished cultures from fragments, scientists reconstruct vanished galaxies from relics like Atlas. Both disciplines remind us that the past is not truly gone. It lingers, embedded in objects waiting to be read. Cosmic archaeology also shifts how we view ourselves. If Atlas is a relic of a galactic past, then our own solar system is not unique, but part of a much larger story. We too are artifacts in the making. One day, long after our sun has faded, fragments of our system may drift through space, discovered by someone else. They will study our comets, our asteroids, perhaps even the husks of our spacecraft, and they will wonder about us just as we wonder about Atlas. In that way, Atlas is not only a relic, but also a mirror. It shows us what survives across cosmic time, and it invites us to imagine how others might one day study what we leave behind. Archaeology on Earth connects us to our ancestors. Cosmic archaeology connects us to the galaxy itself, reminding us that even in silence and distance, stories endure. Atlas drifts quietly, indifferent to our interpretations, but to us it is more than ice. It is evidence, memory, and perhaps even warning. Civilizations crumble, stars die, systems vanish, but fragments remain. All we can do is learn to read them, to honor the whispers they carry from ages before our own world existed. And in doing so, we take our place as cosmic archaeologists, uncovering the deep past written in the dust of interstellar travelers. The needle in the haystack. Every time humanity discovers an interstellar visitor, the excitement is palpable. Oumuamua in 2017, Borisov in 2019, and now Atlas, each has ignited both scientific curiosity and public imagination. But beneath the thrill lies a quieter, heavier thought. How many of these wanderers must we study before one finally turns out not to be natural? How many haystacks must we sift through before finding the needle, an object that is undeniably, unmistakably artificial? The scale of this search is daunting. Our galaxy contains hundreds of billions of stars, and each of those stars has likely ejected trillions of fragments, asteroids, comets, icy shards, into interstellar space over billions of years. These fragments drift silently, waiting for chance encounters like Atlas's. Our solar system is not special, it is simply one stop in an endless ocean. Detecting a handful of interstellar objects across decades is like pulling a single grain of sand from an entire beach. The odds of finding the needle are slim, but not impossible. History suggests that persistence pays off. Before we found exoplanets, many doubted they could ever be observed directly. Now we know of thousands. Before gravitational waves were detected, they were theory. Now we hear them regularly. With each passing year, technology improves. Telescopes sharpen, surveys widen, computers sift data more quickly. What feels like chance encounters today may one day become routine cataloguing, with dozens of interstellar visitors detected each year. Among them, perhaps, the one that changes everything. But what would that needle look like? The truth is, we might not recognize it at first. Oumuamua was odd precisely because it did not behave like a typical comet or asteroid. No visible outgassing, a strange acceleration, an elongated shape. Some scientists argued for exotic natural explanations, others hinted at artificiality. The debate continues. Atlas, too, has its peculiarities, unusual chemistry, odd brightness variations. Each case stretches our categories of normal. Perhaps the first truly artificial object will not announce itself boldly, but will instead lurk at the edge of explanation, a puzzle too persistent to dismiss. And here lies the difficulty. Nature is full of surprises, planets with diamond rains, moons with oceans hidden beneath ice, stars that pulse irregularly. Many phenomena once seemed artificial until science caught up. Pulsars, when first discovered, were nicknamed LGM, Little Green Men, because their regular radio pulses seemed like deliberate beacons. They turned out to be rotating neutron stars. What if the first truly artificial object is dismissed the same way, written off as another natural oddity? Searching for the needle requires not just instruments, but humility. We must be willing to accept that nature may mimic technology, and that technology, if it exists, may mimic nature. An artificial probe could deliberately cloak itself as a comet, knowing that observers would assume it is ordinary. In such a scenario, the disguise itself is the message. The needle hides in the haystack because the haystack is the perfect camouflage. At the same time, the very act of searching changes us. Each interstellar comet we study, whether natural or not, adds to our understanding of the galaxy. Atlas teaches us about chemistry beyond our system. Borisov revealed what interstellar ice looks like. Oumuamua challenged our expectations of shape and behavior. Every haystack we examine is not wasted effort, but progress toward deeper knowledge. The search for the artificial needle enriches us, even when the answer is not yet. There is also comfort in the idea that the needle might already be found, only unrecognized. What if Oumuamua was the first? What if ATLAS is? Our hesitation, our endless debates, are part of the process. Just as ancient astronomers mistook planets for wandering stars until patterns revealed themselves, we may one day look back and say, that was the moment. That was when we first saw it, and we didn't yet know what we were looking at. For now, Atlas drifts by as another candidate, another shard of cosmic history. Perhaps it is natural, perhaps it is not. Either way, it sharpens our eyes, prepares us for the possibility that next time, or the time after, the evidence will be undeniable. The haystack is vast, but the search is patient. Humanity has only just begun sweeping the first handfuls. Time as the true threat. When people hear about 3i Atlas, they often focus on its motion. It moves fast, faster than anything bound to our sun. Its orbit is hyperbolic, guaranteeing it will never return. To most, these are the details that sound dangerous: speed and trajectory, the possibility of collision or sudden disruption. But perhaps those are not the real threats. Perhaps the greater danger is something less obvious, something woven into the comet's very being, its sheer antiquity. Time is relentless. On Earth, we see its power in small ways: rust on metal, cracks in stone, the fading of photographs. Left long enough, even mountains crumble and seas reshape continents. civilizations vanish, languages die, entire ecosystems turn to fossils. If this is what time does in thousands of years, what does it mean for an object like Atlas, which may have been wandering for billions? Think of it. When dinosaurs roamed the Earth, Atlas was already adrift in the dark. When the first stars were forming in our part of the galaxy, Atlas may have already been there, circling in silence. Its surface has been battered by cosmic rays, sculpted by collisions, altered by temperatures so extreme we can barely imagine them. It is not merely a comet, it is a survivor of ages beyond human comprehension, and that survival itself may be the most unsettling detail. Nothing survives so long without being shaped by its endurance. If Atlas is entirely natural, then its chemistry is a record of environments older than our Sun, preserved like an ancient script written in ice. If it is artificial or even partially altered by intelligence, then it is proof of technologies built to last across cosmic time, machines that could outlive civilizations themselves. In either case, the weight of time becomes the real revelation. We humans are not built for such scales. A century feels long, 1,000 years feels eternal. But to Atlas, 1,000 years is nothing, a blink of frozen silence as it drifts. Its journey is not measured in lifetimes but in epochs, and that perspective should humble us. Our questions about its speed or path are fleeting, but its story is written in a language of patience we cannot match. There is also a subtle danger here. The older something is, the less predictable it becomes. Atlas's chemistry does not match expectations, perhaps because it was formed in a time and place utterly unlike our solar system. Its behaviors may not fit our models because our models are young, based only on local data. In this way, its antiquity is a kind of threat, not because it seeks to harm, but because it defies what we know. To encounter something shaped by billions of years is to admit that our science, brilliant though it is, may be like a child reading the faintest fragments of a much older book. Time also challenges us emotionally. When we study Atlas, we are confronted with our own brevity. Civilizations rise and fall in the span of its journey. Empires, languages, religions all come and go while it drifts on. To compare ourselves with such longevity is unsettling, even frightening. What if this is the true message of Atlas? Not that it threatens Earth with impact, but that it threatens our illusion of permanence. That in the scale of the cosmos, we are the fragile, fleeting things, not the comet. And yet, there is beauty in this danger. Just as fossils remind us of life long gone, Atlas reminds us of cosmic ages we never lived through but can still touch. Time is its gift as much as its threat. Its icy body carries within it the memory of stars and systems erased from the galaxy. To study it is to reach backward across eons, to hold in our instruments a piece of history older than history itself. Perhaps the real challenge is not to fear its age, but to learn from it. If Atlas endures, then endurance is possible. If it survives across billions of years, perhaps humanity too can aspire to leave something lasting, a probe, a record, a legacy that drifts as long and as far. Time humbles, but it also inspires. So while its trajectory and speed dominate the headlines, they are not the deepest story. The true weight of Atlas lies in the fact that it has outlived everything. Stars, systems and civilizations have come and gone, but Atlas remains. Its danger is not collision, it is perspective. It forces us to see ourselves as momentary, to feel the smallness of our place in the universe. And maybe that is the most dangerous truth of all, that time itself is the adversary, and Atlas is its silent messenger, reminding us that in the vast expanse of cosmic history, we are the newcomers and the clock has only just begun to tick. Redefining harmless. When NASA and other space agencies announce the discovery of an object like 3i Atlas, they are quick to assure the public there is no threat of impact, The words are meant to calm, to remind us that this is not a world-ending asteroid barreling toward Earth. And they are correct. The comet will not strike us. Its path is well understood, and it will slip back into the darkness without so much as brushing our atmosphere. By the traditional definition, Atlas is harmless. But perhaps that word, harmless, needs to be reconsidered, because not all dangers come in the form of craters and collisions. Some come from ideas, some come from what an object like Atlas forces us to see about ourselves, about our assumptions, and about our fragile grasp of certainty. In that sense, the greatest danger of Atlas may not be physical at all, but psychological. Consider the shock of Oumuamua in 2017. Before its arrival, most people assumed the solar system was isolated, its comets and asteroids confined to orbits around the Sun. The discovery of an interstellar object shattered that assumption. Suddenly, we realized that our system is not a closed box, but a crossroads, with visitors capable of dropping in at any time. That shift was harmless in the physical sense. Oumuamua posed no impact risk, but it was profoundly destabilizing. It forced us to widen our vision of what the universe could deliver. Atlas takes that destabilization further. Its chemistry does not match expectations. Its brightness changes in odd ways. It reminds us that our neat categories, comet, asteroid, harmless rock, are human constructs, convenient labels pasted onto mysteries we only partly understand. Atlas is harmless only if we mean it cannot kill us. But what about the way it challenges our science, our sense of control, even our imagination? Is that truly harmless, or is it a disruption of a different kind? Think about the role of knowledge in human history. Fire was once harmless until we learned how to wield it, and with that came both warmth and destruction. Nuclear energy was born of equations on paper, abstract, harmless, until it split cities apart in seconds. Knowledge itself carries risk, and Atlas offers knowledge from beyond our world. What if that knowledge unsettles us more than impact ever could? There is also the danger of what Atlas might reveal about us. When the public first heard of it, speculation swirled. Is it a probe? Is it natural? Is NASA hiding something? In those reactions, Atlas became a mirror. It reflected our distrust, our hunger for mystery, our tendency to weave conspiracy. The comet itself is silent, but in its silence, we expose our noise. We see how quick we are to fear, how eager we are to imagine enemies, how fragile our sense of truth has become. In this way, Atlas is not harmless at all. It unsettles the narratives we build to feel safe. Even if we set aside speculation, Atlas reveals something more subtle but equally powerful: how provincial our perspective still is. For most of human history, we thought Earth was the center of everything. Then we learned we orbit the Sun. Then we learned the Sun is one star among billions. Now we face the reality that even the small icy fragments drifting past us are not ours, not local, but galactic in origin. Atlas is a reminder that we are not the landlords of the cosmos, but tenants in a vast and unpredictable universe. That realization can feel thrilling, but also frightening. And yet, this redefinition of harmless may be a gift in disguise. True safety does not come from avoiding discomfort, but from expanding our understanding. By shaking our assumptions, Atlas pushes us toward humility, toward curiosity, toward recognizing that the universe is stranger than we imagined. Its danger lies in its ability to make us question, and questioning is the first step toward growth. So, when we call Atlas harmless, we should be precise. It will not collide with Earth. It will not end life as we know it. But it is not harmless to our illusions. It disrupts the way we categorize, the way we feel secure in neat boundaries. It reminds us that safety is often an illusion and that the cosmos owes us no reassurance. A universe that refuses to be simple. From the moment we look up at the night sky as children, We crave simplicity. The moon is a silver lantern, the stars are scattered jewels, the sky itself a dome. Even as adults, we try to hold on to that feeling that the universe can be reduced to clear rules and neat explanations. Gravity pulls, stars shine, planets spin. We want the cosmos to behave like a clock, elegant but predictable. But then along comes something like 3-eye Atlas, and suddenly the clockwork breaks. Here is an object that looks like a comet but doesn't act like one. Its chemistry leans heavily on carbon dioxide, not water. Its light fluctuates in ways we don't expect. Its path is hyperbolic, carrying it away forever. In every respect, it is a reminder that the universe does not exist to comfort us with simplicity. It exists in all its complexity, refusing to fit neatly into our categories. This is not new, of course. Time and again, the cosmos has humbled us. Pulsars were once thought to be alien beacons, their regular pulses too sharp to be natural. Quasars were dismissed as impossible until their true power was revealed. Galaxies lit by ravenous black holes. Dark matter, dark energy, the accelerating expansion of the universe, each discovery shredded an earlier illusion of simplicity. Atlas joins this lineage. It is one more reminder that reality, when observed closely, will always surprise. And perhaps that is the most unsettling lesson. Not that the universe is hostile, but that it is far stranger than we dare to imagine. For billions of years, Atlas drifted in the interstellar dark, accumulating scars from radiation, collisions, and silence. Its survival itself is improbable. Its chemistry is unusual. Its arrival is rare. To encounter it now, in our brief window of history, is almost absurdly coincidental. And coincidence often feels like purpose, even if none is there. This raises the question, what if complexity is not accidental? What if the universe's refusal to be simple is itself a kind of design? Not necessarily the design of an engineer or a civilization, but of a cosmos that thrives on richness, variety, and surprise. Life, after all, is born from complexity. Stars cook heavy elements, comets scatter them, planets gather them, and somehow, out of that tangled web, consciousness emerges. If the universe were simple, we would not exist to notice it. Atlas embodies this paradox. It could be nothing more than an icy fragment from a long-dead star system. Yet even that scenario is awe-inspiring. A shard of another world, older than our own, visiting us by chance. And if, by some remote possibility, it is artificial, engineered to look natural, then the strangeness deepens beyond imagination. Either way, Atlas reminds us that the universe does not bend to our desire for clarity. It remains mysterious, older and more layered than our brief lifespans can grasp. There is also a humility in accepting this. When we call something strange or anomalous, we are really admitting the limits of our understanding. Atlas forces that admission. Its presence tells us, you don't know as much as you think you do. And in that admission lies both fear and freedom. Fear, because uncertainty unsettles us. Freedom, because mystery means there is more to learn, more to discover, more to be astonished by. The temptation, of course, is to impose meaning where none may exist, to see Atlas as purposeful, as sent here with intent. Perhaps that is just the human mind projecting agency onto randomness. But even if its purpose is not designed, it carries one nonetheless. It reminds us to stay awake to the complexity of the cosmos. In its silence, in its strangeness, Atlas teaches us that the story of the universe is not simple, not finished, and not easily tamed. In the end, Atlas may pass back into obscurity, fading from our skies and our conversations. But its lesson will linger. The universe is not a clockwork mechanism built for our reassurance. It is a wilderness, vast and unpredictable, where the simplest answers rarely hold for long. And as unsettling as that is, it may also be the greatest gift. For if the universe refused to be simple, it also refused to be dull. And in that refusal lies the wonder that keeps us looking up night after night, searching for the next impossible visitor.